and time sleep, because we want a delay. And the setting LED equals LED 17. And this is here then. And it's going LED on and off with 1 second in between. So we don't know what LED is yet. We can't see the LED on the board because it's in a box. So this is a bad example for us, but it is a good example to just see what code looks like, right? So let's look at the next one. With very little code, you can quickly get going connecting to your components, connecting your components together. So let's look at this one too. So Python here, and this one, instead we're using button and LED. Yeah, so I'm thinking this might just be a pin where there's a LED and a pin where there's a button. And now I'm curious, and we can just connect stuff up. But just get a LED and a button, right? I think I have it in my drawer here underneath the pizza. Let's get another pizza piece. So that's a half pizza after this, and I will never eat more than that. Though I haven't eaten much today, so I'm actually hungry. You can advance using declarative paradigm along with provide a description of the behavior of devices and their instructions. So I mostly just read the code, right? And we see and we try to understand it, right? So I think it is the way I said, that if we do this, we get a reference to, we set this at 17 as an output device. We set 4 as a motion sensor device, and we have a name for it, a reference. And the same here, light sensor. So, though I would like to see a bit of they connected them. Because the button, it could be, this button could be connected in different ways to this pin. So we need to know a bit more about the functionality. So, though I'm kind of thinking that we'd have like the button connected to the pin connected to 3.3 volts being up, so we connect a resistor to ground, and then we connect a button to 3.3 volts. So when we click the button, we get 3.3 volts there instead of ground. So that's what I'm thinking. Pull down resistor, in other words. So see the chaperone source values for more information. Yeah, so that's the first link, is it? This might be LED button. LED button equivalent to LED source equals button. Oh, you can even do that. So you can set it automatically to do like an event. Like, what do you say? If the state of this changes, this input changes. So though I prefer really having it in clear code like that. And we can also see here what the... And this is like debouncing the value of the button. I don't know. Every data has a value property. Device's current value. Input devices like buttons can only have their values read. Output devices like LEDs can also have their values set to alter the state of the device. And now we're on the Python prompt here. LED is initially off. And it's giving us a reply. And LED on. And then the LED value. So you can read the value also of the ones. Nice and object oriented. So it seems to be like I thought it would work. Here's a PWM LED. So we could adjust the brightness of the LED by PWM. And the pot. And this is an interesting name. We need a list of the names. I want the list of the names. Gimme, gimme. So, we're at the very start of it, right? This is a start. So, the library includes... By the way, let's actually do this. And I'm gonna eat a few bites.
The library includes interfaces to many simple everyday components, as well as some more complex things like sensors, analog to digital converters, full-color LEDs, robotics kits, and more. See the recipes chapter of the documentation for ideas on how to get started. Pin factories. GPIO0 builds on a number of underlying pin libraries, including RPI.GPIO and PICPIO, each with their own benefits. You can select a particular pin library to be used, either for the whole script or per device, according to your needs. See the section on changing the pin factory. A mock pin interface is also provided for testing purposes. Read more about this in the section on mock pins. Installation. GPIO0 is installed by default in the Raspberry Pi OS desktop image, available from raspberrypi.org. To install on Raspberry Pi OS Lite or other operating systems, including for PCs using remote GPIO, see the installing chapter. Documentation.
And it said it was pre-installed on the Raspberry Pi page. That's why we went here, right? So I don't think we need to install it at all. I want to see the objects. API, I guess. Here. The classes. Button. This is just an example. So bounce time. It has it built in. A lot of nice functions. Functionality. Pull up. So you don't even have to set your own pull up resistor there. You can just set it to the pin to default. And that's where we read about, see if I can use tab. We'll have too much food on the keyboard. So we read here that GPIO 2 and 3 have fixed pull-up. And other pins can be configured in software. But you never know how strong these are, but maybe this Raspberry Pi is like a powerful thingy. So it should be good enough, right? Extends, smooth, And input device. Smoothed. TRCT 5000 line sensor. And was this what we saw used? Not here. MCP 3008. So there's lots of devices. Is there not like a list of them? You can't expand this. That's kind of annoying, right? If you just want to see the higher level and not see all those sub thingies. So I'll have to just scroll through it. Motion sensor, light sensor LDR, rotary encoder, oh, here we have a imaged. So button is digital input device. By the other ones are smooth input devices. Did distance sensor, light sensor, line sensor, and motion sensor. So let's actually grab this image, right? And put it. Oh. I by mistake. Oh, it's just a zoom. I was like, I missed my alt tab and did C and this key, and this is actually zoom, and I've forgotten. So let's put this one in the. Actually, let's keep both up. So here we want like an overview. What stuff exists? So this is called input device hierarchy. I'm assuming there's a output devices. So input devices. An image is always nicer, right? This is really just image text. And then we have, I'm sure, for the output devices, here, the same image with outputs. We'll see here. So this is very nice. And let's do devices. And here we have buzzer LED and PWM LED. PWM LED is PWM output device, and these are digital output devices. They're all output devices. We have an angular servo, which is a servo. We have a motor, phase enable motor, and tonal buzzer. RGB LED is in here. And these are GPIO. So RGB LED is probably LED on the board. It's not on the GPIO pins. And all these are composite devices, while these are GPIO devices. Yeah. So we'll have to do a servo too, right? Of course. But we'll see what we'll do today. It all depends on my family, really. I think I'll go down with my pizza because I'm not gonna eat anymore. I almost couldn't finish that last piece. And I also have this falling out of my ear. So the other one actually just turned from red to green. It's charged. So, pizza dog. I didn't use the plate I brought. I'll be back. there. Let's just drink some water too. So I don't have stuff all over my teeth. This is finished, meaning I think it's unplugging automatically. Yeah, so we only have the hard drives here. And I just have to UNES drive H. I'm still not used to having a 20 terabyte drive. That's very nice. Yeah, so it's already unplugged. We can just pull it out and put it back into the Raspberry Pi. So it's going this direction since it's underneath the board, and making sure I won't drop it in there in the middle of it. So, and this is good proof that it's actually off, right? So now we're starting it. You should have something underneath there, right, so it's visible. There. So you don't get the light from the purple light and the reflection. So what is this? It's lighting up. Right. So we found this nice images showing us a very nice graphical overview of all the input and output devices that we have in GPIO 0. It's just too good to be true, this, right? Pretty and nice. Though I think this will probably... Yeah, we need a bit more data. A tiny bit more data. I could assume things and test things, which we could just do, or we could read a tiny bit more. Well, this is starting with a new one, which should have SSH, and it should have the same account. So now it should actually connect. So I think it dropped the data that it's supposed to have SSH enabled when we rebooted it. That's why we made a whole new image. And it will probably reboot a few times at first to do the configuration. So it might not be up yet. So let's do the ping until we see it up. So as long as we see destination host unreachable, we can just continue reading. And if it's too long, I'll have to check it out, right? So it's still, we still got HDMI connected, so we can double check. Maybe we even have to click something at first, but I don't think so. When we enable SSH, it's like this is going to be remote. We can do it all remote, right? We don't have to connect a screen to it to do stuff. So we have this one. It actually annoys me to have that up, so I'm aborting the ping for now. Yeah. So these are some examples. Source values. Alright, this is that. And then we have pot. This is a pot. I really want to know more about this. So I'm going to search for it in input devices here. Control V there, and I thought so. It's not in there, right? So what does it exactly mean? This is kind of why I continue to look. So I'm assuming this is a potentiometer, and maybe that this is some kind of details on what it is. I don't know. and this is PWM LED, setting the value dependent on the pot here automatically. And this is very cool. This is a lot of, we don't have to code. LED source pot values. Alright, also this doesn't have, this doesn't have a port number. This is something special. The way this works is the input device values properties. It's used to feed values into the output device. Source had to be set on older versions. It is also possible to set an output device's source to another output device to keep them matching. In this example, the red LED is set to match the button and the green LED is set to match the red LED. So both LEDs will be on when the button is pressed. So could you not then set this to button, or were they just showing something? Or is this a workaround since we only can set one per each source? I mean, use these for one source. Input device, custom generation output, button opposite LED. So we can also do opposite. And custom generator. Def rand, while true, yield rand int. LED 17, LED source rand. So it will just just fluctuate randomly. Like a light. Like all these fake candles. Let me see. Right? If the iterator is infinite, like while true, processed until the source is changed, set to known. If the iterator is finite and less, it will terminate once all elements are processed. Source tools. So let's not dig into everything at once, right? Internal devices, daytime. That's good to know. We have daytime. So time of day, we can set a lamp on and off depending on the time of day. Right? So we just set it that between 8 and 20 we want this to be on. Daytime when activated. Lamp on. This seems a bit odd to me. That it's, but I guess this is some kind of special thing. Using the DiskUser class like a reference to it. It's still odd. Disk usage, LED bar graph. Graph source disk. This is so cool. So very cool. So we're gonna have like a thing behind me saying how much hard drive space I'm using. If I wanted to, you know. Well, or just any value. But we could always do that like by ourselves, but it's automatic. Demonstrating the garden light system whereby the light comes on in the dark. Yeah, so now we have a motion sensor and a light sensor setting the garden light. I'm like, yeah, all the project we can do. Why do I only have 2 Raspberry Pis? Because we could do all of this also with with DSPs and Arduinos and Arduino Nanos and tinier things than that. And we don't want big, expensive Raspberry Pis for everything. But it looks good. Composite devices. From GPI port, import robot. The value of a composite device made up of nested values of the device. For example, the value of robot object is 2 tuple containing left and right motor values. So it's controlling the steering of a robot then. Left motor and right motor, yeah. Oh. Cool. And controlling them with potentiometers. Oh, yeah. So the thing I'm mostly interested in here is that we have this pod again. I want to know more about this. So let's include the parentheses and just Google this. So, oh. It's not a potentiometer, is it? It's a chip. Where's the data sheet? I must have been blind not to see the big data sheet PDF here. But let's just see. Oh, it's just hopping down. So, microchip. MCP. And we were on 3008. And let's nice. Maybe we want this still there, but we want it bigger still. Bright light. So when will this come in inverted colors, right? In dark mode, dark paper. So 8-channel 10-bit 80 converter with SPI serial interface. So AD converter. I need more information. Sensor interface process control, data acquisition, battery operated systems. I'll not understand this. This is what it looks like. So a fun bit is to program this yourself, you know. It's fun, but if we don't have to, we could use the time for other stuff. And I can get stuck in doing the fun little things that are not really efficient. So we could skip those if we have automatic stuff. The microchip technology. Devices are successive approximation of a 10-bit analog to digital converter with onboard sample and hold circuitry. Program will provide a set of different input pairs of 4 single-ended inputs. Program will provide 4 differential nonlinearity and integral nonlinearity are specified. So this doesn't tell me anything, okay? Communication with the devices are accomplished using simple serial interface compatible with SPI. Devices are capable of conversion rates up to 200 kbps. I guess signal per second. Voltage. So we're going 3.3 here. Low current signs mid operation typical standby currents. 5 NA. Nanoamperes. Microamperes. This is just the packages. So it is analog to digital converter. So it converts a potentiometer value then to a digital signal. Can't the Pi do that itself, or is it doing it? And that's why we have it, because that's what's on the ship, right? Is this why? Do we have these ships on the Raspberry Pi converting stuff, right? It's turning off. Let's do that. Okay, so that's interesting. So I'm curious now about the MCP 3008. Let's go back, and I want the connection. So I can order these from some Swedish stores here. That's not what we want. Maybe we want that. Though we would order from AliExpress and be patient. So I don't want to order them. I want to see their connection with Raspberry Pi. Oh, look. Someone else Googled. So, Raspberry Pi analog to digital converters. So it is probably used in there. So let's just, we don't want to read all of this. Oh look, here's another image. We can see all the things. Yeah, so I end up on this random nerd tutorial sometimes. So I've been like getting their email and just deleting them for a long time. It's just like spam when you get to money, you know. So look, they're doing kind of what we want. Oh, they're using this. They actually need the ship. It's not on the board. So use a potentiometer here to control this like that. We need the ship. So I might have it. It's not like it doesn't seem like an odd one to have. Let's look a bit. MCP 3008. Just go AliExpress quickly and just check. Did I click delete instead of enter? So, one ship. This is expensive. So if we get tiny ones. No, this is just one piece of what? Let's hold lower this. Yeah, so these are kind of expensive. So, I have so many random things though. We might have them if we want them. So I'm kind of used to tiny processors having these built in. Doesn't the Raspberry Pi have any? So if we go back to this article and look here, there's no pin saying that it is an analog pin. So that's probably why these are used. I'm just surprised, you know. I'm sure the ESP has them, the Arduinos have them, I think PICs have them. So Digital to analog to digital. I don't have 877, I think. Whatever, recommended, it's okay. So, pens. EN. Control registers. So this doesn't say very much. Let's not dig into too many details and just go down into something. So I want to make something that functions before I end stream today. So let's continue looking. So Raspberry Pi. Let's do RP, right? And then do GPIO, right? Because I'm thinking I don't want to dig into this now, but I might want to look at it later. So this is interesting, and this kind of, come on. So wiring it. So this is something I would expect it to do itself. But I guess it's more like a PC, which... whatever. So here we can see some example code again. The pot again. And this is like a special, not a normal input line. It's not an input type with a pin number. So, channel 0. So it has a set configuration that it needs to have. Possibly. Since... well, might not. But it says that it is a channel now 0 on this. And... yeah, I want to look more at this in this. It's probably in there in the docs. So, we want to be able to use potentiometers. That it can't is like odd to me, right? Then we were to need a chip. So, as let's see. Do we have this working now? Do we have SSH running? And since it's not projecting it once, let's look at this. It is up in its horrible 4K mode. And I can find the mouse again. So it is set to automatically install and start and run and whatever you want to call it. SSH now. Oh gosh, where's the mouse? Oh, so it is actually disconnected, which kind of says why it's not connected. So I didn't expect to have to do this. So using keyboard and mouse makes this horrible, and I just want SSH working. And now we did the pre-install thingy, and we're going with Raspberry OS because it has these things installed, right? That's why we're doing it. I'm clicking with the wrong mouse. Let's move it. So So let's look. There should be like graphical configuration thingies. I can't read anything. So if we... Right, let's preview this on my right screen. So I'll have to go to the studio mode and open up this and then this. No, it didn't help. So if I go here and then I transition, no. Oh, why? Oh, why? So let's hop to this and hop to this. Now I have it there. And then I can, let's see, preview it to this screen. And now we should be able to zoom. The thing is that I have to preview this to my second screen. Oh my god. Oh gosh, that's crazy. That's crazy. So this, let's close the previews. Close. I'm doing it again. I'm previewing the Raspberry Pi output on my primary screen, and I'm previewing the zoomed version on my second screen, so I too can see the zoom. Look. Now, if I have this mouse pointing there and I move the Raspberry Pi mouse, I can finally see. So programming. And we can see the pixels are not that nice either, right? It's not just me. It's not just my eyes. It's just bad. There's a graphics menu, image menu, VLC player, Firefox. So we don't really want any of this. So I know what I should have done. I shouldn't have installed the graphical stuff, right? Because then I have to use the graphical stuff. Archiver, document viewer, file manager, terminal text editor, preferences. So here we have the Raspberry Pi configuration. So I have to move my other mouse to this area. So let's move it a bit there. So then we can try and find this area. With good thing I can see for the full thing on there. Let's get found where I was. So system, password, host name, boot, auto login, splash screen, browser, and display, interfaces. SSH is on, right? Performance, localization. Yeah, it might just be that it got a new IP when I reinstalled it. So it's not the same machine, though it has the same, you know, it has both the same name and the same MAC. So the same OS. Let's check its IP really, right? Let's check this again because I've never seen this before. So boot to desktop CLI, so we can just set it to boot to CLI here. And auto login too. Why would we want it to auto login? So we don't have to have a graphical interface. Have to click around with the mouse. Serial console is also on by default, and we can't even remove it. Oh, the serial port is disabled. Why? So that's why we couldn't use it, is it? So, serial port enabled. Turn on to enable serial port on GPIO pins. So if we want to use the GPIO pins, then we have to change this, right? So now we know why we couldn't use it, because it was disabled. And also I'm kind of thinking maybe we should keep it going to the desktop. As long as we're not there, right? It takes resources, but this is just a test, so it doesn't matter. And if we really want a slim machine, we wouldn't install it anyway, right? This is just a test machine. It might be good to have that option easily available. Though I'm thinking these options will be available in the CLI one too. Overlay file system. Case fan. There's no such thing. The GPIO. We can set the GPIO. Alright, so if we enable the fan, then we can access this. Okay, get it? I didn't mean to do that. I'm just going to where it was. So click here, locale time zone, keyboard, set keyboard, and let's say set the layout to Swedish. So I tried. Oh, it's just a very long list. There, so we have Swedish keyboard on. There. So that's good to have. Keyboard. I don't care about any other settings there really. Reboot it. Do you want to reboot now? Yeah, and let's check my configuration. So I'm going to close these previews. Let's exit the zoom mode. And let's hop you over here. Let's see if we can manage to ping this IP and see if it pops up. Meanwhile, I will go to my third window and check my leases. Raspberry Pi 161. Let's close it and open it again. View leases. Yeah, I don't think it got a new one. I can just can I remove it? I can map static IP for something, but I don't think I can remove the lease. Raspberry Pi. I can click delete, but I haven't selected anything. Not the best UI in the world here. Anyway, 161 is still unreachable. So we know now that it answers on ping, right? Because we got it before. Maybe you can see it now, but I can't. So it is up. Preview. Oh yeah, so now we have a login instead because I asked it not to automatically. Alright. Fix it. Is it password? Very hard password. So why wouldn't SSH just work? Let's check the IP. That's what we're doing now. So there. I don't care about the zoom and the thingy Madu. Let's just see if we can manage to see the IP here. So IP space A. I can manage to type that. And I can't see this. If we zoom this, it can't zoom when it's on the screen. So I'll have to close that. Preview it again. Preview on this screen. Then I can zoom it and preview this on the other screen again. So much just to be able to see an IP address. So let's see there. I'm here. If I click this, why won't it zoom now? I don't know. So I'm just gonna print screen the darn thing, and let's get the image program. So there's no way I could read this. There's no way. Come on. So here you can see my attempts at previewing. So this is how tiny the text is. Yeah, so it's not just me. It's the computer too. So it. Oh. I feel so stupid. So we talked about fixing the cable, but what happened? The cable is not really there again. So now, let's see. Yeah. I'm thinking it switched addresses or something when I knew that it can fall out. So probably the SSH will work fine too, right? So let's just click this so we're doing the right thing. And let's just close this image. And let's SSH instead. And now host identification has changed. Possible doing something nasty. That's cute. Did you see this? Someone could be eavesdropping on you right now. Man in the middle attack. It's also possible that the host key has just been changed. Yeah, we reinstalled the computer. Please contact the system administrator. Add correct host key in to known host to get rid of this message. So there's also a command. FR, right? The host key is changed. You have this is interesting. I've never seen this. But I guess this is why we have it, right? But I would kind of assume after all the times I've added new ones for the for all the boxes, you know, when you reconnect and there's a new one, because the box is, well, I guess it's not the same. This is not the same either. It just has the same IP and the same MAC address and the same host name. Well, now we have done that. So fix it. If you're on my internal network, now you know the password. So that's, I guess, why I'm never worried about some security really for myself, because I always assume that everything I put in a digital device connected to a network, everybody can see. That's my default from always. So then nothing is new or surprising or, you know. I'm not assuming stuff is secret. Right. We're there. We only have one problem, and that is our cable. I would love to just focus on the Python and the Raspberry Pi. And we should probably do that. But still, let me just check if I have a RJ45 and we can just fix a new one so it doesn't keep falling out, because I will go crazy, right? From missing. I miss it now. I can miss it in 2 seconds again. It will be annoying if it keeps falling out. Det var Raspberry Pi inkopplad. Och så bara jag bara, vad fan så helt SSH till den här för? Så kameran andas ut och bara There! We got it! So, I really want the microscope now, and now we can really do it, right? We have SSH, we don't have to worry about that. I can pull the darn cable here. So, we see nothing. And let's actually look at this instead. So I'm going to take this cable, and I'm gonna put it in the drawer. Because this is the perfect connector for the Raspberry Pis. So we want it accessible. We just don't want it in our face. So I'm sure there I put them. So we'll put this organized and nice in the drawer. And let's move this a bit, and this will fall out again. Do you see it fell out at once? That's why we want to do this. So we don't want to keep being disconnected. We want a new one. It won't look as pretty. It won't be as good. And my eyes like need the microscope for this, because I have a little nice guide I've made for myself, but I didn't find my one of these, so I got my hubby's. I think we have 3 in the house, which is annoyingly bad. So one was my dad's. That's why we have 3. So what I want to do now is to unplug the other end, as I'll be messing with the cables. We don't want like electricity in there. Not that it matters much. It's not a lot of it, but still. Alright. So I'm just gonna unplug the other end of the cable. Meaning I need to reach it. I think it's, I can see it, but it's on the other side of the table. Probably going under it is the best. So let's what's wrong? There. So it doesn't go up if it's not even, and something had blocked it before, so now it's going up. Now I can reach it easier. My little switch. So let's see which one is which. So I don't unplug my computer. So that one goes to the computer, and this one goes up there. So we could really just get a new one. This is a very long one, but it's on a big roll over here. Nah, let's do it when we've started. So the table is up now. This is the bag being squashed. So good. So now we can put the microscope on. And we need to connect its HDMI. There. And now if you go to the microscope, we have a bad view because I have it set. This scene is set to other stuff than usual. So let's remove those. Let's put the rounded corners back on. Filters. There. And then we can go to this one. So those were just adjustments. Those were just adjustments for the Raspberry Pi, since I had stolen the microscope's HDMI. Since this one kept disconnecting my camera that I used for the Raspberry Pi. So let's see, we want not a mega tiny one. There. So there. So I think it's kind of good. And I also changed the arm. I was talking about changing it, and now I have. So this is another arm. This is the one which is actually, this is stable and not just flying all over. This is not going up and down. Very nice. So we can now look at the cable. And we can take a screenshot of it. And let's look at this in the preview on my main screen. So I see the same thing you do. And if we look here at the cable, we can see the colors. And this is what we want to see. We can even make the microscope go down. I should probably lower the resistance there. So we can also just look at the web, you know. But here you can see the broken plastic. The reason we need to do this, because it's too annoying when it falls out. It keeps falling out. I kind of remember these in my head too. I've made a few of them. So let's just first do a screenshot of that. And I'm closing. And we're gonna go to that image program. So this is kind of quick to do. The tools are very nice. So here we can see the colors. It's not very good though, right? So let's actually Google it too. So RD45. I guess a pinout would kind of be good enough, right? So we can see here. Oh, look here. So yeah, so I have made crossover cables too. I think this one has it, right? Just both. So you can see this, you don't have to have a hub or switch in between, you can just connect computers. But this is good enough for us, right? So I need to call my mom too. And I realized time is starting to, oh, also the crossover pinout. So RD5 pinout, A and B. So now what? A and B. So the first, so this is why it would be nice to look at the other one. And we have the image though, so we know what it used to look like. So we have we have this to compare to. I'm gonna put this on another screen and zoom in. So I can see it's brown, and then it's probably brown white. Yeah, so both have that. Then the next one is green. Oh, so it's this one, green, and then I can't really see, but I see something blue, and then it's definitely blue. And then I can't really see anything, then it's orange, and then I can't really see anything. So this is what we need to build, the B one. So as long as it's, you know, the same color on both sides. So now we know what this one had, so we can just do the same again. So I'm gonna cut it. And I just remember how wiggly these cables are. So we're cutting the cable with a broken thingy. This bit. So I do have these plastic pieces too, but as I didn't find my pliers, I didn't find those either. So let's, how much do we need? Something here somewhere. That kind of length, I believe. So let's get rid of the white plastic. And this is a very loose cable, so it will probably be very hard to get it organized. And now I kind of need the microscope, the preview, to see this good. So I have my goal in the other side. So here we can see all the twisted pairs. And we have this thing in the middle that we want to get rid of too, because it's just in the way. So let's cut it off. You can even pull it out a bit there. So now we only have the 4 twisted pairs here. So we're gonna untwist them. And trying to make them straight. So this is what, like, if you do a lot of them, your fingers go ouch. And they also get longer and different lengths from this, right? So the blue ones, and also these, we can see the brown, a tiny bit of brown on that one. We can see this as green and yellow, so we can identify them if we need to, or which we need to, right? So come on. So I'm just like bending them back and forth a bit to make them straighter. So we don't need to make these.
Kitty says, just cut the red wire. It's always the red wire.
Yeah, sure, let's cut the red wire. So now we need to organize these. We need brown on the right side. So we're just making a new internet cable there. Alright. So now we want the brown and white one. And it seems to be this one, right? There. And then we want the green. Then we want the blue and white. And then the blue. Then we want the green. They kind of organize themselves there. Didn't have to do much. Now the thing is just to not lose these. And keep them in order. Try and hold them. Let's see now. Are they still in the same position? Yeah, it looks good. Because if we push this down, and then I'm gonna actually cut a few of them just because they're sticking out extra. So how about the blue one? They're kinda same. So then we just push these into the connector. So here's our old one. We can see what it looked like there. So we can see it's the other way. So it's supposed to go in this way now. See? So not this way, but this way. Meaning we should probably have done it the other direction, but I was looking at the image. So I have this image up here to confirm the order, since I couldn't really see the colors of the connector. And I don't remember them in my head. So, by the way, let's hop back to microscope because I need to see good. And my fingers are dying now from pressure. So usually I'd like to see them in this direction. So let's actually turn it over. Try and clamp down on this and double check the order again. So green, blue, blue and white, green, brown and white in there. And now we want to push them on into the side where we can see stuff, right? So we want them not to switch orders when we do this. So yeah, gosh, that was hard. And my hand is like holding that pressure for a long time. So again, you can see the length has changed. So let's also pull this out a bit. So yeah, it still looks good. I guess it's just to go for it, right? So it's not a lot of space in here. And let's see if we can push them in. And this white thing is kind of big, so it's not all the way in, and the white thing is kind of loose on the cables. That's what I said before, that it's like hard. I can always like push all of it. If I push it instead, I should have done that from the start. It's not really in there, is it? So when we clamp down with the pliers, these things will go into the cables at this place, so they don't really have to be all the way, but at least so both kind of prongs there go in the cables. So I would like to pull the white back and push the other forward, but I'm not going to redo it and pull it out for that. I'm going to try and see if they're in the right position. So we have definitely green, white, blue. That's probably blue, white, green. Yeah, so they're still in the right position. They're all the way in, I believe. Let's do another push there. So I think this is good enough. Then we just grab this and we just put it in the pliers in the little hole and click it in place here. So, and then we just push. Let's actually do this. So it is, I just pushed it in there and just as hard as I can. So there's also one part that pushes the plastic. So this plastic is pushed into this. So it's not only this that holds it in place, but now you can see these are pushed into there. So let's compare to the old one. So if we compare these two, you can see that the metal bits, they're now pushed into the wires. Before they were sticking out, now they're in there, in the wires. So that's, we don't have to like peel the plastic off or anything. And the plastic bit here, it's squished into the cover. That's why I want the white plastic to be this far in, you know, so it's stuck there. So now it shouldn't fall out. We have this. This is what we wanted. The old connector had dropped it, so the cable kept falling out, and now it kept trying to find what's wrong with the IP address or whatever connection, and it was just that the cable fell out. So now we don't have to mess with that problem anymore. So so this is a bit funny, you know, if you push too far, it will go out. So just enough and it will take a little space. There. So I'll put that away later. And this we can just throw away. Bye-bye. And now we have to check that we have connection again, right? So here's the other connector. Let's put it back in the switch. Alright, I raised the desk last time. Maybe I should have again. So click, clicky, clicky. Just a tiny 4-part switch over there. But we could have another lab cable up on the table. At least one. So, now we'll plug this into the Raspberry Pi. And it will not fall out. So, actually I have to open this a little bit. This is always scary. There, now it's stuck. Can't fall out. There we have the Raspberry Pi, the cable. So now we're going to play with this. But first I have to make a call, actually. I have to call my mom and order some food for her. But we'll probably, you can have this up, right? Um, so there's a Keeble alive. Before we do it though, let's go to the right screen and confirm. So it could LSLA, though we plugged the cable out, didn't do anything, plug it back in, and we still have our connection. SSH and TCP/IP, of course, right? Let's just I'll make my call, and we'll continue and actually get some cool stuff done with let's see. So the GPIO stuff. So this. So I'm thinking what I should show when I'm not. Let's just do it quickly, right? Yeah, so we want to definitely do a PWM and other stuff, but I will quickly make that call. We can have this. No, I can't have this up. Let's actually do one thing before I close this down. We still have that on, and we have this thing for that. So there. So I'm doing this, and you can look at. Yeah, you can look at the desk actually, right? What I'm thinking is if I'll be typing something secret, and I might. Not my mouse grocery list, but I will be paying for the stuff. So let's actually hope over here, right? And let's open this up. And let's close the desktop down. But let's also open up this page and this thingy-madoo. So this is what we're doing there, right? This is what we're gonna do, and then I'm gonna call. Let's see. And it's usually kind of quick to order some There, sorry. So I was ordering food for my mom. So there we got an echo because I had the stuff on there. So there. So got some dog bones for a dog here and lots of food. Alright, right. So I'm just gonna add in. Oops. There. She remembered one thing more she wanted to ask, so let's go. We're ready to continue, right? So there. We back. And where did we have this one? Like somewhere here? This tab? So we found this very nice document, and as soon as we found the GPIO 0 here, we hopped into this and read, and we also have put some information about it in our notes. And these are just some simple examples. With the help of these images though that we have here, we can see that this pin number 2 here, or any pin really, we could use them for data. And if we look at this, we have here all the pins easily accessible, and we're currently measuring here the value of pin 2. So maybe we should start with pin 2 so we can see if this changes. We can just set pin 2 to something else. But the first thing we need to do is to hop over to this machine and confirm that we actually can use this GPIO 0 in Python. So before we do this, let's actually hop back here and see if there's any more information. Permissions I see here. So view a inputs. Yeah, so we have checked that it's 3.3 and 0 volts. We can use internal pull up and pull down. GPIO 2 and 3 are fixed pull ups. And while connecting to a single component, so GPIO is safe. Be careful when you wire things up. LEDs should have resistors to limit the current passing through them. Don't use 5 volts for 3.3 volt components like this. Do not connect the motors directly to the GPIO pins. Instead, use a H-bridge circuit or motor controller board. So have a suggestion here. So I guess we will allow the cookies for Raspberry Pi work using motors. So We're not currently using motors, but this sounds fun, right? So, of course, we'll have to connect everything carefully. Right now, we just want to be able to see that we can change the value of a pin. Also, we tested, our first test was to try TTL to USB, as we saw an example of, and it didn't work. And then we noticed that in the GUI, we could see that the serial was actually off. So that was why.
When Insomniac says, best viewers on Weblink.
That was a cool username, actually. Too bad it was just an ad thing. So don't click it. Permissions. In order to use GPIO ports, the user must be a member of the GPIO group. The default user account is a member by default, which is us. Other users must be added, so we don't need to do anything. GPIO paths. The GPIO connections on the BCM 2835 package are sometimes referred to as peripheral data sheet as paths, a semiconductor design term meaning ship connection to the outside world, not word. The paths are configurable. CMOS push-pull output drivers, input buffers. Register-based control settings are available for internal pull-up, pull-down, enable, disable, output drive strength. Okay. This is just another place in this document, I believe. Yeah, it's further down. So let's just skip that. Input trigger filtering. Power on states, all GPIO pins revert to general purpose inputs on power on reset. So they're all inputs as default. The default power states are also applied, which are detailed in the alternative. So this is a good thing to have in our on reset. We have this. Though we will set everything right. Most GPIOs have a default pull applied. Details. So pull states. Right. Let's just leave this. We don't need it in our notes because we will have to check it anyway, right? Or set it rather. Each GPIO pin, when configured as a general purpose input, can be configured as interrupt source to the ARM. Okay, so inputs can be interrupts. Several interrupt generation sources are configurable. Oh, so it reconnected the TTS. Level sensitive, high low, rising falling edge, saturation, rising falling edge. Yeah, so let's not read all of it, right? So what am I mostly looking for now? Is there anything else here that we want? Industrial use. So oh, PCIe connector. So, power button. Oh. The JTOG jumper is located between the RTC battery connector and the board edge. To break out allows your own power button. Raspberry Pi 5. So, mine is a 4, so it doesn't have those. Power supply. PoE. Yeah, we don't need to read all of this, you know. Let's just say we got enough data physical computing. This is motors. If we do motors, let's do something, you know. What I mostly was looking for was if it said any other ways than Python to do it. But I guess Python is kind of the way, right? So let's just quickly look at this. Well, that's cute. Do you see how big these LEDs are? It's on the breadboard. Those are like 1 centimeter ones. So, oh look, they have like cute little examples. And these are not even using any data. Here they're using data. So we have a breadboard, but what we need though is some resistors, some stuff. Let's see what I did have in this one. There's actually a resistor in here. And a LED too, but it's an ugly one. Let's see, what else do we have? Let's go full this, right? So there's a yellow LED in here. Let's get some components to get started. So I'm thinking I had another breadboard with some LEDs on it and some more stuff. So there's a bunch of CDs. I need to decide if I'm just gonna throw them out. Zo. It's just like cars. This is LEDs. So let's get some LEDs. These are ugly ones, right? We don't need that. We don't need this. I have more easily accessible stuff, I'm sure, in the drawer there. USB Arduino displays. No, let's. Yeah, I'll just go and get some stuff in the other room because I'm sure I have this breadboard ready there. Yes, I really think most things are in here now. But this one has a easy button. And another resistor too. And we also have this photoresistor. That could be fun. There's a LED, and this is a LED with actually a resistor on it. So I have obviously used this to see if it's powered. Right? So there's a resistor in this. So if we connect this to this one, first of all, can you see? So let's actually do this too, and put up that, and let's zoom there, right? So let's put so I'm disconnecting these because now we're going to be connecting. I don't have a preview. I need a preview. There. Blurry. So we want the 3 volts. And it's actually not straight up, that's why it looks crooked. So let's connect this one, 3 volts here, to this. There. You can see. And then we do ground with a black cable. And we can take the ground we have right here. There. So now we have 3 volts though. But that's what we want. So the LED might be a bit weak because the resistor is put in there thinking 5 volts most probably, right? So you can see the bulge there where I put the resistor. Yeah, look, I actually did that. That's funny. Yeah, so we can also see I put the length there. The reason for this is that the short leg is minus, and minus is black, right? So we put the long leg in the red one. And if it doesn't light up, I put it the wrong direction. So this is just our power indicator now. So if we go back to the desk, you can see the LED being on. And if I were to unplug this one of these, so that we're getting the power from the Raspberry Pi now, it turns off. So you can see that it was actually on there. So we now know that all of this strip has power. Let's actually move this one to the very end, so it's out of the way. Right, so we know that it's on, it's power. If we were to turn the Raspberry Pi off, this would go off, right? It's always good to know. And for me, this is red. For you, it's just white, right? So, I also have this button here. So, if we look at the microscope again, so you can see better. So this is soldered. Since this is a kind of tiny button, the legs are actually too tight to fit a breadboard. So I've just put legs on it that will fit these. So we can put this somewhere else on the breadboard. Let's put it here. And then if we connect this to this, and these two different pins here, or just one of them to like ground, and the other, we'll see what we do. Actually, we'll probably want to have it on this side since we have our power here, right? So we will connect one of these with a resistor to whatever value we want, or we won't, because there's a pull non-automatic. So what we would usually do, or what we want electronically, is that when we push the button, we have one value, like 1, and when we release it we have 0. And to get that 0, it can't just be nothing, you know? It needs to be connected to something. And then what we usually do is we put a resistor, so like, let's put a resistor from one of the legs. Now this is not a very big one, it's just for LED. So let's put this between ground and it's kind of hard because it's soft legs, so I'm gonna use pliers to push it down. So if we push this one into, I don't know how big a resistor we should have though. So these are like good value for actually it's kind of funny because it's the same value as this one, right? This is like the normal value of resistors. It can be anything, but I usually do this value, and I think I'm not alone. Anyway, these are kind of weak and thin, so let's hop back to the microscope and let's just do it so I can show you. So if we push this into there, and if I would push the other one into the 3 volts, I probably wouldn't want to touch both of them, right? Or the 3 volts, because it would get power. So let's say that we want this to ground. And this is another reason to use the pliers. So I think I can see better with my eyes. So the soft legs, and my fingers are not tight enough to push close to the thing there. So now this side is like connected to ground. There. So what we would do then is we would put a cable on the same side and put this on an input pin here over on the Raspberry Pi. And this would be like, first of all, we're going to just test to see whether this connects. Where did I put that LED? I have a yellow one here with kind of long leg, but it was so ugly. Look at the color of those legs. Whatever. It's not as horrible as it looks, actually. My eyes see it worse. It looks just like they're black. So, as you can see here on these, we have a shorter leg and a longer leg. And we can also look from the bottom. And if I hold it lower, let's actually use this. So I can hold it lower. One edge should be a bit flat. Do you see that? So if we cut the 8 legs off, we can still see that this is the lower side because it has a flat edge. That is the side that's going to the minus, and the long leg is a plus. The round side is a plus. So let's connect this. This is not what we're really gonna do, but just to show you the basics. So as we have minus on the other side there, I'm now going to put the plus leg in there, and the minus leg on the other side of the button, right there. So this has nothing to do with the I'm just looking for a cable. So far it doesn't have anything to do with the Raspberry Pi. This is just basic electronics. So we're connecting this side, this leg here, to, right, I didn't say right, but these are all connected. So this one, this one, this one, this one, and this one, they're connected. So when I connect the red cable here, I connect it to that leg. So this one and that one are connected, right? And on these, the long ones, they're connected the other direction. Actually, I'll go get another one. But I can pull the bottom off. So, let's see, what is this look on the other side? So here you can see the metal connections. So let's go microscope, I guess. This is what they really look like underneath. The long side ones look like that. And the others are connected in the other direction. So this is what the breadboard looks like inside. There. So this is looking like that underneath, and this looks like this. So that's it. Very easy. Logical, right? So our LED is still on over there. We still have power from the Raspberry Pi. If we wanted to turn it off for a bit, we could just unplug these. There. So, but let's build our thing finished. What we have left is to plug this red cable here into the power. Where we can see here, I have marked them with red and black. So this one here, this is power. Meaning, what happens now, I need something tinier to point with. So the power goes from here over to this point and through underneath there, up this leg, through this, and down this leg, through the button that's not pressed, so it's not bleeding electricity right now. And then if I don't push it, so I shorted it now. I shorted the leg and the resistor. And then the button, it goes over here, through the resistor, here. So if I click the button now, it lights up. Do you understand? Let's see if I can make it higher up so we can see more of the view. So this cable, this is not connected to anything yet. So we only have the LED and the resistor over here. And really it should be more like that, right? And I'm showing you nothing, so there. Now we can see it, right? So if I were to short these two, that leg and the resistor, if I manage, then we also short it, but the button is easier, right? I press the button and we get this. Okay. Just a sec. Knock on the door. Yes? Okay. Go in the hall. Vi städar massor imorgon och fixar gris. There. So I realized I didn't get all the things. So this is the current one, and this is in the way. So we still have power. If you click the button now, it lights up. But what we really want is, we don't want the LED here. We want the LED on another one and pass it through. So maybe we want the LED to go on and off when we push the button, right? Add some logic to it programmatically. So we would want first to read when the button is pressed and output it to another place, another pin. So right now, then we would just remove this, and maybe I should have this still here, because it was much better view, right? Why doesn't it update? This is odd. I've never had it not update before. So we have a macroscope activate on off button. This is a totally new experience. It's never not worked. And it's not like we're getting a test image or anything either. So I'm thinking, did I pull some cable out somehow? I'm just reattaching the HDMI here. There. We seem to be without microscope currently. It's not there. Why is a good question. Knocking again on the door. Yes? Okay, but you're off. Yeah, I really need. I a box fell over before, so I have those old phones all over the floor. So, there. So I'm so sorry for all the. This is life with family with kids, you know. I'm the mom. I have to go and get help because I'm saying like you can't ask your dad for food too, you know. Like try and do it evenly. He's like, Mom. So we were doing this. We wanted to do this with a microscope. So let's see if I can try and debug it. It's black. There's no power, right? That explains why it's not on. So I believe I stepped on a wire. And the power for the HDMI to USB converter is not plugged in anymore. So let's actually raise the table up a bit so I can see better. There. And I'm gonna crawl under the table. Where did it go? That goes up. It's not like there's a lot of wires here. Well, there's a lot of wires, but not one's not going anywhere. So yeah, I really don't see anything. I think it's probably USB powered. So it is fastened to the table by cardboard. What am I saying? Like, what do you call them? Whatever thingies. Let's see if I can. It's attached to the table. Come on. This is so annoying. Oh wow. It's too attached. It's attached to the table. So the microscope is power, it's a converter that doesn't. I didn't see any cables. Might suggest that it comes from up here. And it goes over there, which is logical. So let's remove the things. Oh, it's a blue one. It's the blue one. And it's actually slightly attached, I believe. There. So I'm going to do something drastic if it doesn't work now. So there's supposed to be another image up in the corner. Oh, the other one died too. Yeah. Because I unplugged and plugged in one of the main ones. So let's see. I'm gonna hop over to so there. This is now reconnected. My ear said that it has better medium too. Actually, let's hop to the right screen and let's pull up both the microscope and the desktop. So when the microscope appears in the corner there, we can see all of it. So we were just looking at one of the pages here. So yeah, these, do I have these in my, let's actually put these links in the notes while we wait. Let's give it a bit of time, then I'm going to mess with so I think I had input. So why do we have the star here? Why is it showing? Undo, 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 undo. That'll have to be good enough. And output. There. So now I can itch my nose without getting a bad conscience on the camera. Now let's, we're getting it time. I'm gonna go and look at the settings. So first we go to this, then we go to this, checking the microscope source. We're deactivating it, we're activating it, and we do have an image. So we're getting back to life here. So we do have an image here now, which is what we want. This was the reason, but we also want our camera to be alive. So I'm going to the camera source too. So last time this happened, at the very start of the stream actually, I had to unplug both the power and the USB to the camera itself to get it started. And usually when I activate it and it has a connection, it will say like, will become gray, the white text. That's it. It will become gray. So let's go back here. And I'm going to go and mess with the poor camera again. We're starting with just closing it up. Down. Waiting a few seconds. More than a few seconds actually. I think I might have been too quick first when I messed with it. So now it's had a few seconds. Let's see. Yo, what's up? And I'm actually standing now, that's why. So we have everything working. Let's lower this desk again. There. Goody good. So there. We can see everything is working. And I just turned the light on to test it. So I want water actually. So now we can go and look at this again. So to remind us where we were when this started to happen, I had this one went. We had a LED between here and here, so the power went through this cable, through here, through the LED between this and this. Then when we pushed the button, it went through here, through the resistor to ground, right? And now we're going to change it. So instead of that, we're going to put this leg here. So when we push this, let's see. So it will just go through the resistor when we push the button, right? But what if we connect something in between? Let's actually move the button a bit. Let's move it back all the way there, right? So we have space. So we can see this is connected to ground with a resistor in between. This is connected to power, 3.3 volts. And when we push the button, it will just pass through here. We can't see anything. So if we connect a cable here, now if we were to measure this, let's do it. Let's not say we might do it, right? So let's go this mode, and let's take the multimeter. There. Gosh, it's really stuck. There. So we'll turn it on, and we're going to connect the ground here to the ground over here. So when we measure things, we will get a value from there. So if we measure the 3 volts over here, we will get 3 volts. Well, 3.3 is the value. So now, if we measure this point where the blue is, it will show ground, right? When I push the button, it will show 3. And now it will show 0. And now this will show 3. So this is the reason why we have the resistor. So we get, this is the pull, in this case down resistor, right? So we want this wire to, when we push the button, it should be 1. And when we release it, it should be 0. This is what this does. So we can decide the value. So if we were to pull this resistor out, which is a mess, I don't want to do it, but it would be like a very odd thing, right? We wouldn't really have something there. I guess I should do it. Okay, yeah, so we just have to pull one of them out. I'm pulling out the one that's in ground. There. Oh well, we got all of it. So now, when we're pushing the button, we're still getting 3. And we're releasing it, we're really getting 0, right? But it's... it is connected to this, and it's connected to nothing. So it's not as safe. So that's why I really wanted to test it too for myself, because it's a long time since I did it. So we didn't really see anything, but we want to make sure, you know, that it's 0. It's not anything else. And also when it's connected to the board, we want to be even more sure that we set the value. It's not something internal in there that's just randomly has a value. So I'm going to try and put this back. And these are very bendy legs. And I managed to make a kind of tiny place to put it, right? So let's see if I can fit it. Let's remove that one. It's at least there. So this is why I didn't want to pull it up, but I wanted to test it. So I think it's as far down as it goes. And then we put this one here. Oh gosh. I think it's about straight there now. It's far down both sides. So let's measure this again. Then we're actually going to connect the blue wire, which will have the same value as the one we're measuring. Here. Push button, release button, push button, release button. It's going to have the same value as that, what we see. You can see the value here. So when we connect this, we need to first set the pin, right? So these pins here, they have numbers, right? So if we go to the full screen so we can see a little better, we have a lot of them. And we have GPIO and a number on a lot of them. And those are the ones we want to play with. And now we're going to test for the very first time to set a value. And we're actually not going to use our new thingy first. First, we're just going to see if you can set the value of one of them. Which one should we do? Let's do 22. So 22 over here. So I'm trying to get this as straight as possible, so we can see straight when we put the pin down, or the measuring thing down. So let's go to pin 22 here. We're going to set this to output, and well, I guess I could use this hole, right? Because the other one was almost underneath. So now it is connected to GPIO 22. So we want to set it. So for that, I'm going to have to remove my preview so I can see Kelly there. We're going to have to make our first Python program, and we haven't tested this yet at all, ever. I have never done this. So I'm just pulling these out of the way of the keyboard so that I can see something. There. So we can still see the pies on there. So let's go here first. What we did, we did get a lot of information about how this works. So let's say that we want to set it as lead, right? Lead is a basic thing. So the lead, we set the pin as lead. Then it will automatically be a output, right? Because it will set a value of a lead. So we can connect our lead here later. But for now, we're just gonna read the value on the multimeter. So, there are probably examples too, right? Maybe basic recipes. We haven't clicked any of these yet. So, yeah, button. And button. And 2 is a pin here, right? So pin numbering. We're not reading everything, but we had 22 as our example. So they're putting a LED on attached to 17 rather than 11. So now 17 is 3.3 volts. Right, this is interesting. Yeah. This is not the same numbers we have, I think. We have, yeah, so we have these numbers. 6, 5, 17. So this is, the 17 is actually pin 11. So the other image we have. The question is, do we want this image too? This is actually kind of nice, but we don't really need these numbers, right? They're useless. So let's... No. So LED 17, is it the same as GPIO? Yeah, so we need to read this. This is a basic how it works, right? We need to read this. So to learn how the Python works. Oh my god, Callie fell asleep. Come on. Let's see. I guess do this. You can't see it. Not that it matters very much. So it's not like it matters. It's not a secret password. It's one of those medium ones. Nothing important in there. So first of all, we're still live on the machine, right? That's the worst command when you already had Ellis laid, right? So we're on this. So let's make their Python and cd Python, and it's empty, of course, because we haven't created any files yet. So let's do like nano. Let's not just do test 1, test 2, test 3. Let's do pin out, pin and 22, right? .py. So this one will do something with pin 22, and I'm thinking we could change the value to 1010 or something, because just put it into 1, that's where it's already at, right? Or rather it's at 0. You can see 0 here. So if you just put it to 1, that wouldn't be a lot. But this is the whole reason we have this. So we're actually going to start with just getting stuff from the notes, because we already copied some code here, and I can see how this works. So this is kind of similar to what we want to do, kind of exactly similar. So we import GPIO 0 and time, and let's instead do LED 22, right? And LED on, LED off, sleep. It's very, very, very crazy simple. Only we don't have a LED there for now. We only have multimeter listening. So we're saving it, and I guess we run it, right? And I will know if Python even works. I don't know if we need to run Python 3. Let's do which Python. Let's see. So I guess we do Python, and we know it is 3, and then we do like Control C, right? No. It is stopped? Yeah, I think it is that you do to stop it. So I don't think it's stopped. So quit. Yeah, you do quit parenthesis or Control D. Control D is the thing. Yeah, I'm like Control C. That's like background stuff. That's not what I wanted. So now let's just do Python and our whatever I called it. So Python out tab and look at the multimeter.
You need sudo to access GPIO, if I remember correctly.
No, it's actually working. So it's possible that there are some... Right, we were in the GPIO group as this user. That's why. The default user is this user, and it was in the GPIO group. So I don't know if you can see, but we have it switching every second now. So it's working fine. So we can see the value is switching.
Yeah.
Yeah. So this is the first time I have ever used this. Actually, the cable, the connector on the Raspberry Pi. So I'm very happy that it was this very crazy simple to do it. So now we're going to instead put a LED on there, right? So let's stop the program first. There. And now it's stuck on 0.158. So it's kind of like oopsie doopsie. So let's again look at the board, and we're gonna change stuff. So welcome in, Arduku. And that's just a multimeter saying, I've been on for a long time, don't forget me. So I'm gonna just preview this so I can see it too. I should have one screen with just a preview, that would be nice. So you can see our pin 22 that we're using as the output. Just go into the multimeter. But now we're going to put a cable in here. So it is still live, but it just has 0.1 volts, right? So what color is this? Maybe the other one is blue. Maybe we shouldn't use purple. Let's do a yellow one. So see if I can manage to. There, yellow. So let's put the yellow cable here in the other one. There. So this. So I did have more resistors on this board, if nothing else. Yeah, so I stole one of them. Let's just go and get more. So here, instead of like killing my own old thingy, oh look, we got more stuff here. So I already stole like everything from this. So let's steal this thing too, and let's steal the LED too. We could steal the cables too, I guess, if we want to, but we already had some cables. So these were kind of odd LEDs. Alright. So they're very short legs, but they don't like look cut. They're just short. So I should really make more like the ones I have put here, which has, I've just put a resistor in there. So you can just plug it in easily. So we have the button there we're going to use. Now let's put the LED next to it. And let's do kind of the same thing as we did here. But this time we put the LED. Let's see, the lower leg is to the right. The shorter one. And let's also look again so you can see it's flat on that side. So if the legs were cut, we could still see which side is which. So this side, we put the resistor again on this side, right? So let's see if we can push this in now. I need the pliers because it just went bent. I should buy fatter leg resistors. So let's see if I can plug this in now. Holding it like this. So there, and it goes. And as this was to the minus side, oh my god, it is on the side of the there. Sorry. So it doesn't matter where, as long as we put it in the black one, right? So just two thin wires in these. And that one is also much higher than the other. So what we need to do now is to put our yellow wire here, the yellow one that comes from the pin, on this side. And we could have put this on the other side. It wouldn't have mattered, except we would have to turn this one around if we wanted the plus to be on this side, right? But we could have put the resistor between instead of the yellow wire as well, if we wanted to. It doesn't matter. This doesn't have any directionality either. It's just the LEDs, and it's a diode. That's why. Light emitting diode, that's the name. So I'm just getting all the data if someone doesn't know, you know. So now we have the yellow one. It goes still to the multimeter too, but it also goes to the LED, right? So if we now just run the program again, so let's just focus a bit there. The button is not doing anything yet, it's not connected. We just have a blue wire going to nowhere. So it's going nowhere. I'll actually unplug it there. So so if I show you my right screen right now, we're having the preview problem there. So let's run it again. No code change. We're just going 1, 0, 1, 0, 1, 0. That's all right. We could actually have the microscope up there too. So let's start the program. There. So is it running? It is going. It is going kind of quickly. So now I'm thinking, what did I do wrong? Because let's check, because it's not lighting up, right? So it might be that I did something wrong. I can't see though. Oh, now I actually do see that it is lighting up on the camera, but for my eyes I can't see anything. So it is working, it's just too much resistance. So yeah, I can see it when I look carefully. So we should have a lower resistor. If we were going to use this, we would have to lower the resistance for that one. So, but as you can see it, I think it's okay. I should have changed it just to do it. Whatever, let's just continue. So the next step, right, is to not just have it blinking, but let's have it listen to the button input, right? Let's do that. So let's actually look there at what we had. So do I want to move the microscope? Let's get it out of the way so I can actually see my screen. So we had these were the basic examples, and we could also see here that there was a button one, right? So let's get a button. We need to select a pin to put the blue cable into. So I probably need the microscope again, right? So first of all, I need the preview. I need it. I should have a fourth monitor, or I'm like blind here. So we're going to put it here, and I've already explained this why, and we have measured the value as we push the button. So if you missed that, you can just go back and watch it. And now we're going to select a pin where we'll connect this. So, well, let's do like 26. Right, so we have a 26 here. And let's see if I can reach. So currently, really, before I connect stuff, I should really. So it's low voltage, but still I want to. And now we have drawing mode here again for my preview. So we should have stopped the program, right? First. And now let's edit it. So we're going to add the button. So button equals button bottom. And what did we do? What's a number? I can't see. Damn. I'm blind. I need the preview. 26. I should have like remembered that, right? So 26. There. And then we have to not just make it blank, right? We want to do while true. Oh my goodness. Well, that's the way. Let's do spaces instead. So button. No, we don't want to use that. So there's lots of functions for button, and I remember that. So let's go back to the information about the button is an input, and input devices here. Let's go to the button class and see what we have. We have pin pull up. Also, we can read the value of this. And we can still print stuff to our command line to get data about it. It's interesting to see what the default is, right? So it seemed to be default for different pins, different defaults. So bool or known. So it's true, false, or known. And maybe known means different things for different pins. So we'll have to get a list of that too. So active state, bounce time, hold time, hold repeat, and pin factor. These are the parameters. And let's see what we have more. We have functions here. Wait for press or methods. Wait for release. Hold repeat, hold time is held. So here we have a property is held when true the device has been active for at least hold time seconds. yeah, this is nice. So we can assume that the default value is kind of good, right? Because otherwise we'd have to set everything every time. So is held, is pressed, turns true if the device currently active and false otherwise. So is pressed is the current one. This one has a bit, it has to be been held for a bit. The property is usually derived from value. Unlike value, this is always Boolean. So, property pin. The pin that the device is connected to. This will be known as the device has been closed. Property pull-up. If true, the device... I'm now looking for the other one. There's no pull-down. Pull-up worth is set to pin to high by default. Property value returns 1. I can see no pull-down, in other words, here. When held, the function to return on the device has remained active for whole time seconds. This can be set to a function which accepts whatever. I don't need to read all. When held, when pressed, when released. So these are like events, kinda. But I just want to know if it is pressed. So is pressed is what I want to check. So we want to make an if here. To click. So if button dot is pressed, yeah, so there, sleep, and we always set it off. So it will only turn it on when we press the button, but then it will turn it off after a second, and if we're still holding it down, the button is pressed, then it will keep blinking. So if we release it, it will just go off. So if we were to do this one, if it will just freeze at the current state, it could stop it on too, right? So that should be okay. So it is property is pressed, it's not a function, and it is always a Boolean value, so it's true or false. It can't be known. We don't have to check for anything else. So if we run this now, and we should probably have the microscope not on my floor, but on the thing. So let's look at this. And move this a bit away so we can see better. And let's actually make this a bit bigger, right? This is like the main thing. We want to see what he does. And I also want to see because I might not see with my eyes. So, if we run it now, button is not defined. Alright, so I didn't change the import statement. So we need to add a button. There. So nothing is happening, but when I click the button, I think it should blink probably. No? So I don't even remember if I finished connecting everything.
It was blinking.
It was blinking. But it was maybe... There it's on. Yeah.
You pressed it.
Okay, so there it's blinking. Oh, so it's blinking when I'm not pressing it. Right. So what did I do in the code? Let's look. Do we want to abort the program? Yeah, let's just do it. I'm not gonna do another SSH just to be able to look at the code without stopping it. So, if button is pressed, LED on. So, to me this sounds like if the button is pressed, we turn the LED on, right? So, it's pressed. And now I'm like, how many equals do I do in Python? So is it 2? And Python has uppercase, right?
You should turn off the LED at the start of the program just so you know the initial state.
Yeah, sure, we can start it off. Oh gosh, yeah, so I don't know the copy commands
Because
for.
maybe you stop with the LED on.
Yeah, but doesn't matter really, right? As it's still going always off here in the true loop. There's just a second before it would turn off anyway. So it wouldn't matter. So we need to Pythonify the white space there. So we're saving and we're running it, and it's supposed to be off. And if I manage to push the button, so now it's doing it the way I wanted it. When I push the button, it's blinking. Only true and false is wrong for me. So let's explore this. So the default state of this is somehow not the right one. So we can see here what is blinking. The default state is 0. And this is the LEDs. So let's move it to the blue pin. And since I have this on the microscope, let's go here. And let's plug this in here. So we can see that this is indeed 0, right? So meaning it should be false in my mind. But maybe it depends on what pin it is, and like some pins have 0 as true. Or rather like, yeah. So the default state is false. Or the default state is 0. When I click, we get a 1. If you can see that, it's 3.3 volts. And it's blinking. And if we look at the code, which I can't do at the same time, unfortunately, we can always cat it. So we can see it at the same time. So let's board it. And let's look at the code. So now I added a false. Instead of button is pressed. So if button is pressed is false, then LED on. So we got it backwards. But it might be that pin 26 just behaves this way. But shouldn't it know that and change it in the code? So that button is pressed is actually... Yeah, so we could change this by just changing here what the values are. And then the code would fit. But I still want true to be 1, right? So it's just a tiny quirk that's nothing to do with us really. That's just how it is. So what's next? What do you want to do? What should we do now? So we know that we can use servos. We might not have the chip to do analog to digital. So I'm a bit surprised that we probably can't do analog to digital like built in on this. We need a chip. And when I checked, it was like $4. So it's not like $0.2. So you just buy a bunch. Right. Yeah, we can always look at their examples, right? And see if there's anything interesting to do. We can look at their basic recipes and advanced ones. So you're looking at my floor currently with the microscope. So. So we had the output, the input, and here's the recipes. So we just skipped ahead of it, right? They're putting a LED on a pin with a resistor. And this is the first example they had in the first page for GPIO 0. So they didn't have any more there. Alternatively, LED blink. Oh, look, there's an actual blink. Maybe we can even give it a interval here. So variable brightness light. Okay, yeah, the PWM. We wanted a PWM, right? So instead of it going on and off, we want to PWM it. Let's add PWM, only we don't want this. 0, 0.5, 1. What do you think? Pulse, LED pulse. Yeah, let's just add another F. So we now change it to PWM LED. And there's special pins that are PWMs, so we need to change it.
You can add
If we go to our
PWM
notes,
for some 5 seconds if you hold the boot on for 2 seconds.
Okay, add a special functionality like that. Right, we could do that. And we could do that without programming it intensely ourselves. We can use the functions that are built in. But what I'm thinking now is that we need to check which pins are the PWM ones. So you have PWM on 12, and we have PWM, I'm assuming 17 or whatever they had, right? They had PWM LED 17. So since these are set PWM, I think there was another one here, 13. So this one, 12 and 13 are PWMs. The other ones are not. So what if we do PWM 17 as they do? Or PWM 22? So let's try and just say that 17 is a PWM LED. I would never have tried that myself if we didn't have another number than these. Because I believe this. That's a stupid thing to do, probably. So, there's also a pause here. So we could use these commands. I was just going to replace the code. Should we have another one? We can put another LED. I have millions of LEDs. Well, not millions, but thousands, okay? So, I think I have some stuff easily available here. So, let's get another color. That's a green one. So ugly stuff here. So green LED. And we need another resistor. Did I have another one here somewhere? Yeah, so we could always get input from this too. But we'd need analog in for that. So now I want to check all my chips. It's not impossible, you know, that I'd happen to have one. So I think this is, these chips are from like some kind of kit. And the analog to digital converter is not impossible. So, but if it were to be the right one, that might be a bit hard to know. So, let's just focus a bit. So I don't remember all the numbers, you know. But I think I'd recognize the one we were talking about. So I'm not gonna check all of them, just the ones here, because it would take all day. I should have like an inventory. So there were also the 4-pin ones. Oh, 455 there. And another one. So those we can have fun with too. Oh. Okay. Also we could play with audio, but let's see. Here's some resistors. So let's stay with the same. So here I have a lot of buttons, the ones that I've soldered these on. So if we wanted more buttons, we could just take these. So I'm thinking, let's not use these resistors. I'll just go and get it. Unless we have something very easily accessible here. So more of the buttons. But those I haven't soldered or put the shrink tube on. Look. So since we had a few more stuff here, we could look at these two. Oh, that's a pick. A 628. Those are fun. What's this? I can't put it low enough. I wouldn't be surprised if we use... No, not another 555. So... we could do like also like digits, one of these. That could be fun. I'll just go get some resistors. I think that's nicer. And also I'm curious if it has like sensor stuff built in. But I guess most of these are analog, right? So this is not really at all the thing for that. We need digital data, meaning more advanced things than just a simple sensor without any logic. That's too bad, really. By the way, this is the most scratched part of my table. So didn't change anything, but a bit of it, right? The zoom. Right, I have this too. Oh, nah. Let's keep the Arduino intact. I'll go and grab something else. Let me just consult my resistor list. And this, I think these are actually, are they the same? No, they're not the same. Oh, so that's why this one is so low. I just assumed that I had them on the board with LEDs, you know? But I just grabbed something, probably. So that's 330, I think. But let's confirm, since I actually made notes on this recently, right? I put in my notes my little favorite image that I had on my desktop. And we have it under, not under hardware. So I should sort this up too. But components, resistors. So here we have our little 3, and the brown for the 0. Oh, a calculator. So I'll have to add that to my links, I guess. But I'm kind of happy with the image.
Online calculator tongue.
Yeah. So if we do here orange, brown, we'll say 330. Do we have to click to calculate? Oh no, I got selected yellow. I totally failed this. So brown is there. It's on.
TMKDK says, I learned the color code in my head. They are not that hard.
So I've used these since I was in like 8th grade. And I still don't remember them. So I don't think there's much chance of me ever doing that. So I kind of guess, you know, I said 330, but I didn't trust myself, right? So I'll just get the box where I have the 100.
Just follow them like the rainbow.
So I wish my kids would want to learn this. I think actually I have a lot of exactly that value. So we can see I think I bought a roll of them maybe. So is this all 330s? I don't know. Let's look at the microscope again.
Since 95, but only took me 5 minutes to remember.
Yeah, but actually I had the interest since before that.
But I forgot the values after a few weeks. Smile.
Yeah, I've learned them several times, and I do this at work too, and I still don't remember them, so that's life. Alright, I have a lot of loose ones. So let's start with these that are just loose. And the bottom. So they seem to be like a bit random. So something desoldered. So orange, brown. I think that's the only one, but we only needed one. So
TMKDK says, I learned them by associate them with stick that had the same color like 3 sounds like tree, and they can kind of be like corn when you draw them on paper.
I guess the thing is that I don't care about remembering them. If I did, maybe I would remember them, you know? But I don't really have any reason to remember them, as it's just easy to look every time. So maybe it would be easier to just remember them, but I've never felt the need to. I've never felt the need to remember the resistor values. And I kind of know that it's black, brown, you know. Or measure them. Yeah, and it's kind of nice to measure them too. So I did, when we did this build, Where is it? We built this on stream just a bit ago, and I checked the values.
Use SMD anyway.
Yeah, and those you don't have colors on. So here, so I checked the values, and we got a wrong one, and I was like, I just from reading it, you know, myself, I was like, this is not in the list, is it? I must be wrong, right? And it was 1,000 ohms, 1k ohm instead of 1 ohm. So this one is supposed to be 1 ohm, and now the tiniest one I had, was 10, which is not good, because it doesn't work. So I was thinking we should build this on a breadboard and try it instead. So we can build the same thing on a breadboard and see if we can make it work. So that's like a $1 or $2 AliExpress project probably. So you can't expect much.
5% is easy.
5%. Yeah, the blue ones are harder to read in the colors. I actually have a very cool image of that. I think I put it. Did I put it in here? So the red and the orange and the brown with the blue, it's like impossible, right? Impossible. So we're gonna put another LED, and I guess we use a microscope again, right? So instead of watching the dust between my keys, let's move over here. And let's put another LED next to this. And we can compare this here. See? Oh, yeah, this one had a different value. So it is a different value, and it is also lower brightness. But since I only saw one, I could have gotten one from the papers, but you know. So this one is actually a bit sturdier, and I can actually push it down. By the way, should we put it close by, right, so we can see it all? So let's just put it a few pins away. There. And then I think this still has its legs, the right length, kind of short, but let's just confirm that we have the flat side there of the LED by the short leg, so we know that we're supposed to put it this direction. So let's just see, that's the short one, right? Short one towards minus. So now you should be able to see all three things, is my hope here. And if I also up a bit, you can see all things in the camera. So we need another wire too. We have yellow and blue. Let's do green. It should be visible, right? So green with a green LED. I didn't even plan that. So should we do one of the PWMs? I'm kind of feeling we should do one of the PWMs for this one, since it's why? So it was hard to push down for some reason. Well, this is a cheap breadboard. I think it was probably the wire. Whatever, that worked fine. So now we go into one of the PWM ones, and I'm just gonna look at this again. Where's the notes? Right, should I put like this in my links? So this is the original one. I don't think I'll ever use it because it's easier. It was harder to click those things than to just calculate it in your head. Right? Let's skip it. I'm sorry. I'm sorry, I don't see the use. We want to go here. We want to check the 12 and 12 and 13. So let's go 13 so we can have them all on the side here. So 13 we'll use. I'm just currently looking for, here's 22, here's 26, and we have 13 here. So it's just 2 steps from the blue wire here. So the blue one is a bit bent. I took a too long wire here. So 2 steps on 13 there. So let's put this green one over here. On 13.
Electrodroid is also a smart way to calculate the resistor and other stuff. I mostly use it for pin connection.
Electrodroid, I don't know what it is. Is it a URL? So when I started with this, internet didn't exist. At least not like for normal people.
Yeah, an app.
Oh, it's an app. Yeah, so I actually have an app for resistors too. If you want to, you know. So this one is green. It doesn't look green. Oh, I turned the light off. I know why. It's because right, look there. It's lighting up. Let's actually close it down again. So this is just a reflection, so it's hard to see if they're on. It's hard to see if they're on there. So the program is not on. There. I kind of recognize it, but it could just be that it's so many apps called Droid, and Electro sounds like a nice name, right? But I have the photoresistors and you see it, but they're not very good. It's safer to do it yourself. And you can't really measure it if it's in a board. So, or you can't. So power still on here. I'm like, what was I doing? I'm having the preview on, so we can't see a thing. Let's add stuff now. So I'm adding them in number, and we're calling this PWM LED, right? Equals, and I have to check what the thing was called. But it was PWM LED. And then we had the function pulse. Then pause. Import pause from signal. There's a new thing. So now I'm very curious what signal pause affects. If it affects both LEDs or only the PWM. I'm kind of thinking the PWM, but you never know, right? So let's put these in our code now. So, oh my god, I clicked space and it just hopped the page up. I have no idea where on the web page I was. Yeah, so it hopped actually up. Camera, yeah, so...
I think you can use sleep instead of pause.
Yeah, so we already use sleep, but pause will probably switch the blinking, automatic blinking off. So you see that the LED class has a blink function, right? That's automatic, and the PWM LED, let's see here, it has pulse. So I'm thinking we just start the pulse and then we pause the pulse. Probably. Because it's in the signal. Right? So this will be interesting to see what happens. So first we need to import it if we want to use it. But let's type finished first. PWM LED And we did put it on 13, right?
TMKDK says, there are many ways to do it.
Yeah. Have you used this? Or are you just playing around with the thoughts of it? So let's get from signal import pause. And it was lowercase. And this is uppercase, and this is like first. It's not logic to me, right? It's bad naming, but it's kind of cool still. So now we'll just add. Let's invert it. Let's put an else here, and let's do lead dot not lead pvm lead dot pulse there, and there almost ended up being a semicolon at the end of the line. I'm trying my best here. So we don't know what pause does. So this is interesting. So what does pause do? Will this be inverted? These two, and we're gonna remove the false because I put the lead on. So it's supposed to pulse when we don't hold it. When we don't hold it, when we start it, the green one is just pulsing. And then when we press it down, the red one is blinking. Okay? With the manual. And we could also put this lead off in here. But let's just try this for now. We don't need to change that to make it more complicated. Not that it's complicated, but just checking for syntax errors and forgotten colons. There. I'm sure I would make one of those, right? So Python pvmlet not defined. Yeah, so I didn't import it. So we need to add it to the list. Lead pvmlet there, and then we run it, and the green one is pulsing. So will it stop when we click the button? Will the whole program pause? What will happen? So it's all paused. The execution is paused. Nothing more is happening.
The red turned on.
Yeah, because it turns on first. So, yeah, you can still see the screen. So if we abort the program and we look at the code, so when we did pause here, we turned the LED on first, and then it paused the whole program, meaning this was still pulsing. And we just have to set something else in the PVM LED to stop it first. So you can watch in my floor there while I actually need to see the screen. So we need to unpulse it instead. And we'll look at output and search for PVM LED and check the functionality of this, or the methods really. So off, on, blink, pulse. There's also time options here. Background. Toggle the state. Off, on. So I guess that off is what we want, right? So if we go back here, and we replace our pause, which paused the whole thing. So we don't want this. Let's just delete this. And this was just a test because it was in the program. We could have kept the parentheses. And let's go off here instead. So now it shouldn't pause execution. But now we know the signal pause means. It's just froze. And I probably could have clicked the program. Like, this is not intended as I have to be in the terminal and click stuff, right? I want this background. So Control SX. And there. So we're back at the right spot and we're running the program. And it's pulsing very nicely with the PWM. So the next thing we do is to switch the values, right?
If you want toggle, you can also do LED equals LED with the syntax for the compiler you use.
Okay, isn't it LED value? Wouldn't it be LED value? Because LED is the whole object, right? And LED is actually with a capital L. We didn't call it that, but it doesn't matter. So let's just continue. We're gonna click the button and see what happens. So holding the button, it's paused again. Oh, so I must have called it the wrong name. I'm not used to Python like this.
It is WebLink. TMKDK says.
Yeah.
The LED include the value.
Oh, did I do only off? Oh my god. Yeah, of course. So did I just do off? Oh, it's because of the pause, right? So I just replaced what was there. I didn't think of this. PWM LED dot. So there, and you can just suggest if you don't have to check before. So now we click, and this is blinking. And then we release it, and we have the nice pulse again there. Oh, I like that pulse. It's pretty.
Nice.
So the question is, it finishes a pulse every time, right? So if I click in when it's on the top, it goes to the bottom first. So pulse actually means do a full pulse. It doesn't mean keep pulsing, right? So we could really remove the pausing from there, probably. But it could also be that there's a 1 second delay. So 1001. Yeah, so 1001.
The green is pulsing.
Yeah, but I'm thinking when it's aborting. Yeah, I think it finishes a pulse every time. Even if I click it just when I released it, you know? So we don't even see the green yet. So I'm thinking this function, it's or the method pulse, it's not like asynchronous. It doesn't go parallel with our code. It's pausing the code execution and doing its thing. And I think that's what it is doing. Let's make the pauses like very short. So let's change it. So sleep 1. I don't like when it's not milliseconds. Why is it milliseconds?
Yep, as long as the if statement is true, it will do that and go out of the if statement after.
So we'll probably not even see the blinking there, but it's just to make sure that the pulse is not aborted. I don't think it is. So if we run this now, and the pulse is going very quickly there too. Nice. That actually means something. And we can't really see the difference now. So this means that it's not. It's actually running our code, right? So let's now increase it instead. So let's change it. First of all, this is the first time I tried this. 0.1 worked nice. So let's do 3 now instead. And explore how this works out. So it does several pulses in the same speed as when we had 1. So if I just click it in the middle of there, 1001, there's 2. So one, 2, 3. 1, 2, 3. 1, 2, 3. I'm too quick. So 1, 2, 3. 1, 2, 3. 1, 2, 3. Yeah. Well, it's hard to say. But obviously the pulse has the same length now, right? So we didn't really affect that. Was it before it actually aborted it, right? So when we put it on 0.1, when we turned the pulse on, and then we turned it off again, or we waited 0.1 here, and we got to the next turn, it started the pulse again, and it started the pulse, and it started the pulse, and it started the pulse. So it is asynchronous. We know now. That's nice. The 1 was getting a nice value. So what's the next thing we do? Or rather, we could have that up. What do you want to do now? Did I say something more we could test? So we only have digital in. Yeah, so I think this is actually digital. I thought it was analog, but I think it's digital. So I wonder what it can do by itself without, you know, us adding stuff. Let's look at more examples, right? There was examples.
Humidity sensor.
Yeah, temperature and humidity. So if we just look at this, here we had sensors, you know, it had line sensor, pin line sensor, infrared proximity sensor. So what is this kit? So if they mean this, we have that. We can get one of these from the box. If they mean this thing, I don't know. So this isn't IR, is it, right? Come on. So yeah, yeah. So I don't know if we have this, but we might. So we see a little ship there. So it's probably digital. So here's the ultrasonic distance sensor. Line follower sensor. That's an odd thing to have it integrated. Is that what they're talking about? Line sensor? Okay, yeah, so then it's probably this thing then. So there's probably LEDs and photoresistors in these or something to follow a line. That's not a good thing. We don't want to do that anyway. Motion sensor. So let's look at this. So I probably have lots of kinds of those. So Raspberry Pi any version, Keyboard, mouse. Oh, this is what you need except for the kit. Temperature, light. Sensing movement. So if we click sensing movement. Oh, they're giving us code. No, it's a PDF. Okay, okay. This kind of thing. 3 leads. So
First sensor.
I'll look in my drawer. Let's see. So we have lots of stuff. So I don't think anything in this one. Oh. So I probably just have a bigger one of those. We have, you see, we have lots of different thingies. And I know some of these say digital. And lots of them have ships, right? So this shouldn't be just analog. And it can't do analog. But I'm still like, every time I think of it, it's like, what? What? It's like the tiniest processor has that. Yeah, so we have, I don't think we have that. I think these are just 555s. Yeah. Gosh, I can't read. Oh, max 3232. Okay. This is 80 tiny 85s. So, nothing in those at least. Yeah, so I'm very surprised. Why doesn't it have that? It's very odd to me. You know? Why? Why? So, let's see if we can find anything else. I might have something in the other room. Yeah, exactly, but this is like in between. So you have this header with the cable, you know, or the pins, so you can connect stuff for being like low level. So we can't do that. Let's close these down. Then what's next? Light sensor. So yeah, so we have capacitors. LDR.
You can buy an ADC or ask for a sample.
Yeah, they had even a ship name, so we looked at it before, but it was less like $4. So it's not like I will get 20 of them just to have. This glass repeatedly charged the capacitor. The time for reduction change will vary according to the light falling on the LDR. Let's give me an image of it. Why didn't it have an image? So I guess we will copy this and we will search, and I want an image. Where did you get that idea from? No, but I want to have more than one at least if I kind of break it, you know. Right, so they just mean, okay, yeah. So, but I was thinking analog, but this we have, right? We have it with a conversion. This is one of the things that I said, that we have a chip here, so this must be digital. So I'll go back to the boxes. They're not being put away. And let's see. So I do need the glasses for this. So where did I put them? Right here, just behind the mic. So in the shadow of the mic. box? I think it's the next one. Maybe it was that
You
one.
only need this computer, you can use it.
Oh my god, now this headphone died. So please tell me more about that when I can hear again. So I can probably hear again. So let's see here. So let's touch. So they have the same layout for several things, and they just change what's in the front here. And that's why I have to go through these. So here's a different one with a different thing. So, and here's the same design, but with a speaker on it or a mic. And the same design, but with a like this thing. So moisture sensor. So I feel blind. Let's look at my little notes. So yeah, those are
You
Hall
only need
sensors.
some analog this switch at some point like a thermostat you can use in comparator.
Yeah, but you want the analog values in, right? That's the reason why you have an analog sensor. You don't just want like on off. So we could just so this kind of says do this or nothing, right? And we don't want to do this or nothing. We want to do lots of stuff. But maybe the Raspberry Pi is not the real good thing for this. We could just put the ESP in instead, and we would have better. So flame sensors. Here's laser emitters. Yeah, so I see no. They're somewhere. There are somewhere. Maybe they were in the first box, so I haven't looked at that again yet. So I feel blind. Where is it?
FPGA do also not use that because it is only gates.
FPGA. So FPGA what? These are like motion sensors. So I'm sure I've seen those, you know? I'm sure I've seen those. Here we have digital temperature too. So this is a digital temperature, for example. So I have like everything but those, it feels like. But maybe I do have them somewhere. Maybe. But not right there. So now I won't find the glasses next time I need them. Yeah, so I can see like a converter here probably, and this and something to trim the setting, right? But I only have this. I don't have any shift connected to it. So we'd have to desolder the other ones and hope that the analog convert DC well, the converter here works without the thing. So let's continue the list. Distance sensor. And now we're probably there. So let's do this. It's the easiest way, right, to find things. So we want images. I clicked images. And now we got this one, yeah. So I even kind of recognize the name because it's all over them. Because they're big enough. So let's see if we can use this link since it had yeah. Let's we had to fix the cable before. Hello. So my kid's knocking. Just a sec. Yes, Mom. Oopsie. So my kid came and said good night, which is good because he's getting to bed in good time. Well, better than me. It's past midnight. How did that happen? So now I see the differences here. So let's grab one of them. So something we have, and that's very easy to find. It's not like a million similar ones. So, and this actually has
You can
3
always
ships.
use an Arduino to consert an analog and send it over by SPI or UART.
Yeah, but then I could use the Arduino for everything, or rather use an ESP instead, right? So, microscope. Oh, that's not the one I wanted. Let's... Maybe I zoom too much here. I just want to preview. There, and now I can see it. And there. And I'm gonna hop back to the page. Yeah, right here's where we just search quickly for these. And when I did, I didn't even know which one it was, so here. So now we actually have a hardware component that works, right? But let's hop back to the microscope so that I can check the pins. So I think I'm probably gonna take an image of this, right? So let's screenshot this.
Analog processing takes time that WiMOS processor for video output have it as extern.
So the chip doesn't even have any text. So there's 3 of them on this one. And only one is name. No, we're not gonna read this. Too much electronics. So there. I think it took the screenshot. Let's see if we can paste it. So, and I will have to like get up tomorrow, so this is good enough. So there.
Cool.
Let's just remove this. And let's check this out. Extend smooth input device, and we have this in our notes here. So input devices. Here's the ones they had, and this is where I feel like this is not a lot of them, right? So it's obvious that this is not the optimum device for input.
Before going to bed, so it will be at you seen.
Yeah, so I ordered from AliExpress, so it will take maybe 1.5 weeks at least before it gets here anyway. So I don't think that would make much difference. We'll see. So we could hop over there. But I'd like to compare a bit and see if there's like, maybe you
You
can get
also have
3 for
electronic company
cheaper.
in Sweden.
Yeah, but they would probably cost 100 Swedish crown instead of 30. So it's, or maybe 150, right? Or maybe 200. So I saw when I was looking for like, I got a mail about a Christmas sale, and I clicked it and I was like, oh, so a Arduino Nano costs like 250. I'm like, okay, how much are those on AliExpress? So when I bought mine, before they increased the postage fees, they were like, well, this price. But this is probably a lot of freight for this. So, but you still can get them kind of cheap, right? So at stores,
Arduino is
they
also
take
in
so
the
much
middle of the
extra.
platform. Not
Yeah.
only the chip.
I know. No, the chip is not it. So this is on my Arduino, right? So no, that's the wrong board. This is Arduino. So I have several of these Arduinos. So let's do there instead. This is the Arduino. The Arduino is not the chip. Arduino is the layout of everything.
Dooku says, that is the Admiral.
Yeah. But it's an Arduino on a breadboard. So you have
Admiral is the chip. I mean,
yeah. So the chip. So let's see if we hop back to the
TMKVK
microscope.
says,
So here you can see.
my first Arduino I got from Sweden because Denmark did not have them yet that time.
Oh, okay. So here you can see the Atmega 328. And as I said, I had a few tiny ones here in the box. So I'm looking in the wrong box. So the cool things about the Atmegas and the Attinies. So here, let's see. So this is a teeny 1885, and it's kind of the same thing, only if you need a lot of output pins, a lot of memory, or if you just need a few pins, right? So it's very nice that it's so flexible. So, but this is the one that's on the Arduino, on the like common ones. But let's continue. We have this up here now, right? So before I have to go to sleep, because I have to go soon. So let's go back. I was just checking the current price.
Even with PWM for LED.
IO extender even with PWM. IO extender. So I've used like shift registers, but those don't do PWM. Let's hop back here. The distance sensor requires 2 GPIO pins, 1 for the trigger, marked trig on the sensor, and this is why we have the image, right? So we know which one is trig, and another for the echo, marked echo on the sensor. However, a voltage divider is required to ensure the 5 volt from the echo pin doesn't damage the pi. Wire your sensor according to the following. Yeah, so I'm kind of thinking, I don't think that I'm awake enough, really, for another project. When I realized we're closing up to 1 AM here soon, and I'm a bit tired. I'll have to go run components and put this. But let's do this next time, right? So maybe Monday. This is our next project, right? So is there a link for this? Let's copy this link and let's put a continue here, right? So that's the link, and let's actually copy the header too. So distance sensor test project. Alright. And we're going to do this next thing to do. Right. And this is here. It is ready. I'll just put it on the board somewhere. So that we can, we'll probably want the cable to this so we can do other stuff with it, right? Not just have it pointing to this. So we can actually see some values.
School AliExpress takes often 2 months here to get here.
Oh, okay. So I ordered some things last week and it's already arrived, so it's kind of quick. I have 2 things waiting for me at the post office. It's not like I buy a lot of stuff on there. A lot of cheap stuff, right?
Maybe it was with an EU, then it takes shorter, but that is pretty rare.
Okay, okay. So for me it's not that rare. 2 months, I haven't seen that in 10 years. I don't know.
Duku says.
Yeah.
AliExpress usually
2-3 weeks.
2 to 3 weeks.
Yeah. That's probably good.
I am also in DK.
Mm. Yeah. So I haven't seen 2 months. Maybe it's just one company.
I often buy from Mail Supply.
Okay. I don't know. It's probably a Danish company. Maybe. So what do you think about time? Okay. So I'm kind of going to look at what tabs we have up and checking a bit of data before we stop. So here I was just looking at what is the MCP. Okay, in Denmark. So yeah, so I was debugging the SSH when it was the wire, right? So I put a new connector on, new RJ45 with an actual plastic thingy to hold it in place, and now it's not falling out again. It was worth the time, right? So here we just have a few images, but let's see what this is. I just clicked a few of the images to get, but I started with the one from actually Raspberry Pi, and we continued from there. We haven't needed to look anywhere else. So this is for an Arduino. We can accept those cookies. Okay. Yeah, so there's of course stars in Sweden, but they're usually, we have ElectroKit, for example. So this one, we have a lot of stuff. I think this might be where I ordered my pies. Yeah, Alpha used to be great, like 20 years ago. And you could just go pick up stuff in their storage shop. But now it's just a mess, it seems. There's pages a mess. Messy. I'd rather wait a bit from AliExpress.
Was where I got my Arduino from in Sweden.
Ah, nice. Yeah, so Raspberry Pi Pico 99. So let's just compare now. Raspberry Pi Pico from AliExpress, right? Maybe we can copy the name so I don't have to type it. I'll have to click it first. So we want to check this exact thing, and it should be short enough. Oh, this is annoying when that pops up. So 99, 112.
She stopped, so I have to get my component elsewhere.
Oh, old lady in the city. That's nice. So apparently this one was kind of good, right? So we can see here 85, but there's no freight charge here. And it will probably be expensive. Here's free shipping for 74. So it is cheaper here, right? But also if we click this, we don't know exactly if we're on the right one. So we have to click something to see.
She was also over 90 years before she stopped.
So actually this one seems to be more expensive than this. So maybe these actually... Also, there's like Christmas prices, right? On Black Friday, these were doing like... Every day, they lowered the prices for a certain number of products. So it got lower and lower and lower. That was kind of fun. Though, I didn't want to buy any of the things, So... by the way, let's actually...
The most common repair fix component not for specialist hobby.
Yeah, so I bought before from Shell & Company, you know, that store, like kits of different random components, and lots of it I never used, and lots of it was just trash, so, like, lots of different screens, and they had no ships, some of them, and just, like, pins, yeah, old stuff. But there were also, like, kit of capacitors, you know? And kit of... So it's more like normal things that you could possibly use. Let's search for this on ElectroKit, because it might actually... Oh my, I failed to copy. So, Control-C. Yeah, I'm feeling I should go to bed before I try and put the components in the right place, not to burn the Raspberry
I looked under
Pi.
Raspberry Pi distributor where they sold to find them in all EU.
So here you can see they're 55 in Sweden. If I just want to buy one, I probably have to pay freight too here. So it would cost 84, right? So if I buy one from here, let's click, let's do free shipping. And let's do kind of low price. Oh, it's these. That also means that I have other things that I might want to click on the same order. So here you can get them for...
She almost ran China price.
Okay. Yeah, so I guess if you have a low number of products, you could just buy, like Arduinos. You can buy a lot of them kind of cheap. So we could buy 2 of these here, for example, and add something else. So I've got like, these could be Christmas presents for the kids. I don't think I need that. Actually, I think I have that already, so I don't know why I put it here. It just looks cheap. And we don't need that either. But this looked kind of cool. The only problem was it's only male. The females were out. So this looked like useful, right? So, but I would want both. Are they back in? Ew.
They're also the other than DigiKey. It start with M.
Okay. So the problem with this thing is I can't search here, right? So you have to go and search. So if I click this, and I want this, and go to AliExpress, search it. If you have any tips for this, I'm happy. Maybe they're cheaper to buy this way anyway. But that thing with several,
Now
it's
they have
usually
a EU
cheaper.
site and a US site.
Yeah, so a lot of shipping here. Yeah, Mouser. So let's click a few of these so it knows we're interested in these, right? So we want to look at those. That's not what I want. Those are what I want. Can't find that page. So let's go back here now and update this page. And hopefully they will pop up. They did. So it's a bit of a mess to use that functionality. So I think I had the mail. Oh, where's the information? So add to pics and USB mail. So you ended up in my shopping here, and this one kind of looks like a female, but it's both. I don't think it's both actually, right? So, but if I order both of these alternatives from this one. Oh, so this one is 22 and this is 39. This is one piece of type A, male, female.
To be lucky, not all chip works. They sometimes scam chip by removing number and put other number on top.
Yeah, so I'm thinking they're both. So that one is 1 and one is 2. And this is what I want. So when you're checking a cable that I was doing the other day, it's so much easier to have this. I used a solder connector and grabbed on with a hook to measure them. But if you have this, you can just attach the cable. Very nice. So definitely this one is going in my thingy. So let's remove the other one. This.
Also, often the component they sell it is often product component that have failed the test.
Okay. I've never had any problems at all. Except for this one. I don't even know if I bought it though on AliExpress. But there was a wrong resistor. And if you buy like a robot kit for $10, or no, for like $2, and then the pins don't really fit in the wheels and you have to mess about, right? And maybe some components are a bit off. But that's because it's extremely cheap. If you buy like reasonable prices, then it's usually just good. I haven't had any problems with any like ships or anything like that. Never. Really. So I bought a lot of stuff from them. So 5 pairs, male, female.
Often they test in out of one lot, and if just one fail, they trash them all and then China sellers sell them to buyers.
Oh, whatever. So, if that's your experience, that's sad. But that would kind of mean they're like bad people. I don't really think so. Though, it's of course, the quality is not as good on some things. Some other things are just, you know, people like in Sweden in the store, they have so many other things. They have to pay for the rent for the expensive store and things. Oh.
FixerBot says,
welcome in.
S1 Ren official brought 23 friends to the party. Go drop them a follow.
Woo. Thanks for the raid. Now I can't stop. Now I have to continue, right?
TMKVK says, Dick, translated from Dutch.
So, thank you very much for the raid, Siren. Thank you so much. And we have been playing with Raspberry Pi. And everybody follow Siren if you're not already. Great streamer. Great hacker. Yeah. So, we were looking a bit at AliExpress here. Kind of running off the stream, about to stop, and now I have to show you what we've been doing. So, we have got this Raspberry Pi here. This is a Raspberry Pi 4B with 8 gigs memory. We have this connected just to check the values here. So it's on. We were going to do a project with this next time. Currently, we've been running this program. When I started, I didn't know how would we communicate from Raspberry Pi OS that I never run because I only run Kali on my Pis, and I just got this cable. So we've connected it yesterday here to the Pi through a little hole to this little board thingy with where we have all the pins here. Let's see. So we can zoom, so we can see all the connectors here very nicely. GPIO IO extension board. So, and we've been looking at this little project here. Let's move this up a bit so we can see a little more. So, focus. There. So, that's what we've been doing. So, we learned that there's this thing GPIO 0 for Python that's installed by default. And the default user also is member of a group called GPIO that has permissions to do this. So we didn't do much. We just started Python. We first added a LED, and then we just checked the values with the multimeter to see that it changed the value. And then we added a button, and then we added also this PWM LED. So we just start here an infinite loop. We check if this button is pressed, and if it is pressed, actually this is like reversed, but that's the way it is. Then this will pulse, which is the PWM LED, and otherwise, if we're pushing it, this LED will blink because we're turning it off every time here. We're waiting 1 second, so we can just save this and run it again. And now we can see the pulse. It's a very soft, nice pulse, right? And if we now push the button, we see this one doing a more digital blink. So 1 second, and we'll also see, depending on where I'm actually doing. Now I'm checking the value of the button, right? So let's check instead let's do the pulse. So we can see the values going up and down here. This is just a power LED. So let's put it on the other one that's more digital. So we can see I've been like explaining all the electronics, how it works, pull up and pull down resistors, all the things. If you want to go check the VOD later. It's also on YouTube. So let's click this now. So we have 0 now on this, and now we'll see this be more on off. There.
Trusty Ape says, it would look cool on analog voltmeter.
Yeah. Should we get one? I might have one. I don't know. I have an analog over there. Yeah, I do. I think so. Let's see. So there's like a knitting machine in the way here. Yeah. So, why not, you know? You mentioned it. It's a bit dusty. So this was my dad's. So, we could check this. So why not? I think I switched the cable because it was broken. Yeah, that's ancient. And I have an even more ancient just amp meter. So it's really cool. And they also have a power supply with the same age. but as it's working, you know. So let's actually see, was I right?
TMKDK says, all my analog meter is more for decoration lol.
So I'm not sure now if this is actually a power supply or a meter. It's probably power supply, right? When I'm thinking about it, because it has both. Yeah. So we won't be able to read anything through this because it's. But we should get
I
one.
used them under my education.
Yeah. So I guess my dad did educate me. So I have a big. There. I have a digital multimeter with the old numbers, you know, with this like light bulb tracks in it. That's very cool. So we could get that one, but it won't be as cool as a meter going this.
Trustee says, vacuum tubes?
There, it's a bit heavy stuff over here, and I don't want to drop it, but I can try. So I need to clean this out a bit. So, books. Books leaning towards this. And let's see if I can grab this. So, this is what I need.
But I still use my analog and digital oscilloscope because analog is just faster for something when you know what you are looking for.
So, this is what it looks like. Kinda cool, eh? We could plug it in. So it's set to volts, and
Trustee says, that's cool.
Yeah, it's really cool. I love this kind of cool stuff, especially if it works, you know. So one of the power supplies, the potentiometer isn't really working very well, so it's going when you turn it. So if you set it to something and then, so I'll have to see if I can find a replacement. But that's a cool project too. But that's the kind of thing that wears out, right? So it's not very odd. So this is probably older than me. So first of all, let's give it some power. And let's see, I think there's a AC-DC power switch. And there's on. So here we have AC and DC.
Fixerbot says,
DC
New
supply.
follow M3B7E. Less than 3.
So here we have 0 volts. And since we're just using these, we can just plug in. So I should probably pull these down because plus 1 k volts, check 1 volt. So let's just do plus minus. We're not doing 1000 volts. So
New follower Trusty 8. Less than 3.
thanks for the follows, guys. So what do you think? It's 0. Let's actually move the keyboard, right? Because we want to see this good. So keyboard can be a bit squiggly here.
digital oscilloscope should have a reset button, not an auto button, so you can reset after you had to measure some specific for next time you use it.
So now we can see the values changing here. Let's do the other one. That's actually pulsing automatically. So we can definitely see the difference between the digital and the analog one, right? So these digits are so cool. They're crazy. Right? So this is almost cooler than something going like this. I think so. So, also, it's on 200.
Still digital, I see.
Yeah, it's digital. Yeah. So it says digital multimeter. And I can see the height changing. I don't know if you can do that. So if you look at it from the
I
side,
was thinking you was showing the scale.
can you see how the digits are in different heights? So, what do you want to do?
Trust me.
We could do
yes.
something else.
I almost can smell it. Reminds me of school loan.
Oh, school. This kind of thing in school.
Some multimeter have a scale in the bottom.
Oh, yeah, so here's the scale on this one. So, 200 millivolts to 20. So I clicked it from 200 to 20 now, and it's changed. So I'm thinking if I put it on 2, we'll have it like this instead.
I mean
So-
water scale.
Yeah. So, whatever. What will we do now? I guess that I will disconnect this again. But it was kind of cool to see that it still works. And we should get like... I'll have even more to clean up tomorrow. So another thing that we're doing, by the way, we're looking at this rotor. And we've collected USB to TTL here, and we've started it. We managed to abort the boot process and started looking at stuff, but I haven't managed to find anywhere in memory where we can like read stuff out, because it says a memory address, and when we like dumped that data out, there was like nothing there. Maybe I just have to dump a lot, because this is kind of a new thing. And it's a lot of data. So I don't know how much it was. If it was... Yeah, I don't remember. So it was kind of a lot. So we'll have to explore that one more and see. So otherwise we've been doing Advent of Cyber earlier. Doing a lot of different things. But it's always fun to play with electronics, because you actually, it's still building Legos, right? Of all these things. So, and we also have, see if I can not drop this. So we have, this is an ESP32 cam. So we're going to have to make like a program for it to put it somewhere, like by the door maybe, or whatever we want to do. And maybe we'll make some like smart home thingies. And then we have, this is another ESP. We have lots of them. And then, what else do I have? We have the soldering station here. Yeah. So I'll just put this somewhere safe. There. So, yeah, so I put it on the honeypot we're making. So it's just got Debian so far. So we're going to install, probably we'll do Teapot on it to start with, and then we'll see what happens from there too. It's like just a ready-built bunch of different honeypot thingies. So, yeah. So, maybe. What? Should I do something more before I get to sleep?
The
What do you think?
UHF generator IDF home was with radio tube that had to be calibrated every time I was planning to build in PLL, but I sold it before I got that made. The same model was even in the ALF TV show in the 80s.
Oh. Yeah. So calibrating things doesn't sound very fun. So this is still on, by the way. So maybe we should stop the program. What should we do? So like the last thing, we were looking at AliExpress stuff. Partly I wanted like a few things. So we were looking for this. So MCP3008, because this is an analog to digital converter, and the Raspberry Pi doesn't have that. And I'm like, what? Seriously, this advanced thing when everything else, all the tiny processors I have here. Here's an Arduino too. So they all have analog to digital pins, right? But the Raspberry Pi doesn't have that. So maybe we'll have to buy a few of these to play with too. And that's why I put 2 here. And then it's just stuff I already had in here. Yeah. We'll be checking through whatever I had up. So next time we're going to, I found one of the things that it actually could
I used
do.
my DIY 1 GHz counter to calibrate it.
Okay. Yeah, also I have a digital oscilloscope that we haven't used a lot, so we should probably do that. What I was going to do first though is to make a ground connection on my radio just behind the desk, and pull a cable and fasten it here so I can just plug in ground for it. Because it's kind of good to have, right? Just generally too, that we don't have outlets with ground in this house. So where were I? I was going to the notes. So next project, next thing to do with this. And here's the only sensors that it really has stuff for. So the GPIO 0 seems very cool, but it's also limited in this.
Ground in kitchen and bathroom.
Yeah. Ground in the bathroom. So those plugs in Sweden, we only have the 2, and it's like 110 instead of 230 volts there. So it's a special outlets. Anyway. So I'm thinking maybe we can use the output device, not these, you know? And instead of PWM LED, we can use PWM output device. Though there's a servo here too, that's kind of what I was thinking about otherwise. And here we only have these sensors, but smooth inputs in that device. Okay, yeah, so of course we have ground in some, right? So the special connectors, it's possible we have that. So like the heating for the house and stuff. I don't remember. And also we definitely haven't connected to the box because you have to be an electrician to that, and made our own outlets in that room at all. So you know we haven't done that, right? So on the other side of this wall, there's actually, maybe we should just pull a wire through the wall for the actual stuff.
It'll help to fix light switch or lamper without a face finder.
Oh my god, that's crazy. Don't you have like standards in Denmark that you have to have certain stuff? But maybe it's old houses. Like this, right? I don't think they will be allowed to. This is from the 90s. So that's why it doesn't have ground. Let's actually take this one as an example. So I'm just trying to unplug the one. This is what they look like here. So we have ground on the sides here. So that was a digital multimeter. Very cool numbers. So even that was grounded.
The house was built in 72 and the standard was made in 70s, but maybe the
Yeah.
electrician did not there.
Maybe. Yeah. So these were just some examples. I'm kind of feeling finished, and for this project we need to let's click the link so I don't have to think, right? So we have to do a voltage divider and stuff, and I don't want to mess up because I'm tired and it's 1 a.m. right? So what time is it? 0, 1, 1, 2. So I don't want to mess up and break my Raspberry Pi because of that. But I'm just too tired to put stuff in the right place.
Still running the ceramic fuse box.
Oh. There, let's see. So what do you want to do? We can do something else. I don't want to wire electronics anymore because I'm too tired for that. It doesn't mean I can't do anything. I have unplugged this, but we can still shut down the machine. So
But no lightning protection
let's
so my
just
PC died this summer because of thunder.
So let's shut the Pi down. No lightning protection. Oh yeah, but that's like I have a my cable. I've just got a fuse in the cable thingy splitter. I think I have two actually. One that's just a box with a fuse, and then one in the splitter, or one of the splitters. A lot of cables here now. So I should probably like turn off the microscope, right? And desktop. And this is just our normal
Often they have all the
Kali.
protection in the electric box outside, but sadly not this time.
So now it's sleeping. And we can turn off the power to there. So I saw the power go down of the network, so it's sleeping. So I have to. It's a bit annoying that I have to click off and on, but I saw that the Raspberry Pi 5, so they have an actual button connector, so you can actually have an actual power button. No, I'm awake. Let's see. What can we do? So, am I too tired to do Advent of Cyber today's day? So, before, when I started stream, I did the first one, and I've been streaming for 10 hours and 44 minutes. So, maybe it's time for the next one, right? So, let's see. Probably I'm too tired, right? This is not the room. If I don't even know where to click.
But we also had over 30 lightning over this small city.
Oh. That's a lot of lightning, but maybe not for... Nah, maybe not. So, yeah, so today is web timing attacks. Nice. No, I've done this one. I was like, is it another one with the same thing? So the only reason this is not marked as done is because I didn't click complete on the last one. Where balances shifts and numbers soar, look for an entry in open door. So this one we want to look at, so I don't want to forget about it. So WebSocket is the next one. It came without buffering. It came without lag. So what do you think? Am I up for this? Am I tired enough? If you say you're tired enough, then maybe you're not up for it. What do you think? We will just do it. It's not like I'm worried about thinking. I'm worried about recording a video when I look like this. That's what I'm worried about, you know? Wow, let's do it, right? Have you all done it already? Let's see. So we have, it's not a split screen, making me very happy. I'm gonna read all of this if we do it. So, exploitation. Navigate to the box. Do burp. And then they do the very long explanation. And intercept too. And we're changing the user ID there. So maybe I shouldn't cheat by looking at it before manipulating the message. So they're all red now. So I was saying, why are there no red ones or just one red in the first bit, right? And then we got like red, 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 4 in a row. That's nice. So flag 1, flag 2 is what we need. Down here too. So it doesn't look like much. I guess I'll just start reading. This doesn't look like it's very hard, right? Or needs brain power. So I'm not up for doing the box or anything, please. I was going to stop streaming, but now I couldn't when the raid came. Let's actually... So we still have burp on from the other one. It's been on. No, I closed it down. Good. Good. And... let's just start the VPN. There. We don't need this. Desktop, so you can see my passwords and stuff, right? What was I doing? So I'm just starting Firefox and burp because it takes some time to get started. So, am I crazy to stream for 10 hours and 48 minutes? Should I ask that even? Maybe that's a stupid question. So I want to have something to drink with all the reading. So burp is up, Firefox is up. They just waiting for that IP later. So D13 WebSockets. It came without buffering. It came without lag. The story. The sockbus was packed with exploits and hacking. Today's treat an app which allows where's car tracking. May your malware adapt? Well, that's their suspicion. For Glitch and Mixkitty, the proof was their mission. Wares are all about security. The Glitch discovers that an app is illegally tracking the cars in Wareville. Not many car thefts in the city warrant such an extreme measure. He reaches out to Mixkitty to investigate. Investigate and identify how the application is tracking them and leaking users' possessions. Yeah, you're all welcome to join the Discord. I saw that it popped up there in chat. Learning objectives. Learn about WebSockets and their vulnerabilities. Learn how WebSocket message manipulation can be done. And connecting to the machine. before we move forward, review the questions in the connection card below and start the machine button. 3 minutes at once, right, to get the website up. So let's just start reading. So, introduction to WebSocket. WebSocket let your browser and the server keep a constant line of communication open. Unlike the old school method of asking for something, getting a response, and then hanging up. WebSockets are like keeping the phone line open so you can chat whenever you need to. Once a connection is set up, the client and server can talk back and forth without all the extra requests. WebSockets are great for live chat apps, real-time games, or any live data feed where you want constant updates. After a quick handshake to get things started, both sides can send messages for an hour. This means less overhead and faster communication when you need data flowing in real time. Traditional HTTP request versus WebSocket. When you use a regular HTTP, that was the IP appearing. Hop, right? So let's just copy it. While we're there now, I'll probably be further down. All the way there. So let's just get started again. Where were I? So, when you use regular HTTP, your browser sends a request to the server and the server responds, then closes the connection. If you need new data, you have to make another request. Think of it like knocking on someone's door every time you want something. They'll answer, but it can get tiring if you need updates constantly. Take a chat app for example. With HTTP, your browser would keep asking any new messages every few seconds. This method, known as polling, works but isn't efficient. Both the browser and the server end up doing a lot of unnecessary work just to stay updated. WebSockets handle things differently. Once a connection is established, it remains open, allowing the server to push updates to you whenever there's something new. It's more like leaving the door open so updates can come in immediately without the constant back and forth. This approach is faster and uses fewer resources. So, what are they doing? Kicking balls over a ping pong table? I don't know. WebSocket vulnerabilities. While WebSockets can boost performance, they also come with security risks that developers need to monitor. Since WebSocket connections stay open and active, they can be taken advantage of if the proper security measures aren't in place. Here are some common vulnerabilities. Weak authentication and authorization. Unlike regular HTTP, WebSockets don't have built-in ways to handle user authentication or session validation. If you don't set these controls up properly, attackers could slip in and get access to sensitive data or mess with the connection. Message tampering. WebSockets let data flow back and forth constantly, which means attackers could intercept and change messages if encryption isn't used. This could allow them to inject harmful commands, perform actions they shouldn't, or mess with the data set. Cross-site WebSocket hijacking, CSWSH. This happens when an attacker tricks user browsers into opening a WebSocket connection to another site. Ooh. If successful, the attacker might be able to hijack that connection or access data meant for the legitimate server. Denial of service, DOS. Because WebSocket connections stay open, they can be targeted by DOS attacks. An attacker could flood the server with tons of messages, potentially slowing it down or crashing it altogether. What is WebSocket message manipulation? WebSocket message manipulation is when an attacker intercepts and changes the message sent between the web application and its server. Unlike regular HTTP requests that go back and forth one at a time, WebSockets keep a connection open, allowing constant two-way communication. This is what makes WebSockets great for real-time apps, but it also opens the door for attacks if proper security isn't in place. In this type of attack, a hacker would intercept and tweak these WebSocket messages as they were being sent. Let's say the app is sending sensitive info, like transaction details or user commands. An attacker could change these messages and make the app behave differently. They could pass security checks, send unauthorized requests, or alter key data like usernames, payment amounts, or access levels. For example, imagine a web application using WebSockets to handle money transfers between accounts. If an attacker gets hold of the message before it hits the server, they could change the amount being transferred or even send the money to a different account. That was my first thought there, right? Since a WebSocket connection happened in real time, these changes would take effect instantly without the user or server noticing immediately. This kind of manipulation can also lead to more significant problems. Hackers could inject harmful code or try to get higher level access. For instance, they might change a message to give themselves admin rights or insert malicious commands to take control of the server. What makes this attack so dangerous is that WebSocket connections often don't have the same security protections as traditional HTTP connections. Like end-to-end encryption, which encrypts the request body of the HTTP request using JavaScript, using an AES key or RSA public key stored in the JavaScript file. If developers don't add vigorous checks like message validation or encryption, it's easy for attackers to exploit these gaps. By tampering with the data being sent, attackers can cause all sorts of damage, from unauthorized actions to full system compromises. The impact of changing WebSocket messages depends on how the app uses them and what kind of data is being sent. Here is a breakdown of what can happen. Doing things without permission. If someone can tamper with WebSocket messages, they could impersonate another user and carry out unauthorized actions, such as making purchases, transferring funds, or changing account settings. For example, if a WebSocket manages payment transaction, an attacker could manipulate their transaction amounts or reroute the payment to their own account. Gaining extra privileges. Attackers could also manipulate messages to make the system think they have more privileges than they actually do. This could lead them to access admin controls, change user data, view sensitive info, or mess with system settings. Messing up data. One of the significant risks is data corruption. If someone is changing the messages, they could feed bad data into the system. This could mess with user accounts, transactions, or anything else the app handles. They could change things in real time and disrupt everyone's work in circumstances such as shared document or tool. Crashing the system. An attacker could also spawn a server with bad requests. Spam a server with bad requests, causing it to slow down or crash. If this happens enough, the system could go offline, causing serious downtime for users and businesses. Without good security checks, this kind of message tampering can lead to anything from unauthorized actions to the downloading of an entire service. Exploitation. Navigate to. So let's copy the link. And we have Where Will Car Tracker? So I think my phone, it's been all 11 hours on stream. I need to just reconnect it because it's not behaving. There, now I can switch screens. So this was just the last Edward of Cyber day. So, Where Will Car Tracker? Your vehicles. Glitches car track. Community reports. McSkitty, the city center traffic is looking good. Come visit. And we can send stuff. Oh look, stuff is happening here. Going through Santa St. All clear here. My reindeer stopped to eat some grass. It's been 2 hours now. Well, it's fun at least, right? So, I'm moving really slowly today. Also, SC Street. Okay. So, Santa Street and another car accident. Cool. So, we got an ad in here even, making it realistic, right? Alright, so we have malware too, but I guess I can't read all those, right? We will be stuck all day. So, if you're using the attack box on your browser, yeah, so we can just skip a bit here on burp. Yeah, so let's go to proxy. And let's not do that because we're not in the attack box. So we need to intercept, I think they wanted us to. Yeah, here it says proxy intercept, because I saw that before when I was just scrolling through it, right? So let's do that. So we're getting constant messages. It's being connected. So let's go. Yeah, so I always go to the history. So let's just clear the history first. And yeah, so I'm like, what? It's new, got a new look. I mean, I never use the intercept really if we don't have to. So I use the history. So now we actually need to. So let's click the track button. And let's look back here and see what they want us to do. I'll just there. So, sorry. I had these in my ears for so many hours. I'm actually gonna switch ears. So this is so the TTS won't get an echo. That's why I have these. So, right. So go to your browser, click the track button. So we did that. Burp proxy will intercept the WebSocket traffic as shown below. So intercept is on. And we have a message here that we got to client to server request. So 42. So is there more? 42 is a very good number otherwise. I don't mind. Yeah, it starts with 42. And then it says message, text, car accident. Right. So we should probably do this to server. There we have it. So this is just one of the messages. Track user ID 5. So they want to change this user ID to 8. And then click the forward. We're just getting a longer and longer list here. And we can see that all of these are actually the sites. So it's not only sending this WS, but also all requests. So it's sending requests, polling, with different keys there. So let's change this one. And I'm like, oh, I can't change it. Right, I did intercept now. I can change it. So there, and forward it. And I'm kind of assuming we're supposed to take intercept off, but let's just follow their instructions. Go back to the browser and check the community reports, right? Okay, okay. So let's go back here. Let's actually turn intercept off, cause nothing. So maybe I was just too slow here. This. Oh, untrack. So we're doing untrack. Then we're doing track. And we're intercepting. So this message to server. Oh, it's not sent. So we need to send that first. Let's forward that. Here, track user 8. There. And then we forward this. Let's forward that too, otherwise we probably won't get anything, right? So to client, to server 3. Yeah, this is just the normal messages. So we're not getting any special message here. Go back to your browser and check the community reports. I think someone is tracking my car. Did I do something wrong? I don't think so. I didn't actually read the text. I just skimmed it. So let's actually read it. So close the window and enable the proxy intercept. Go back to your browser and click the track button. Bird proxy will intercept the WebSocket traffic as shown below. And here, change the value of the user ID from 5 to 8. And click the forward button. It only looks a bit different now. Go back to your browser and check the community reports. And we're getting messages, right? Though only if we forward them. So, oh, there it is. So we just had to wait for a bit. It was a bit slower. So it's still not appearing, but I saw the message. So why isn't it working? Let's update the page. So of course nothing is happening because we have intercept on. And we're gonna intercept again. And we can read it here, of course, but it's like a bit annoying. And maybe it's like a timing thing that we need to turn intercept off at once and they didn't mention. So let's forward this one and actually read the messages here now. So McSkitty, here's the thing we want. So let's copy it from here instead. Flag 1. And we forward that too. And here it's saying, I think someone is tracking my car, style, color to client. And I click forward. And then we do transport polling. Tracking update time. So I'm just gonna paste that that flag while I still have it, so I don't forget. Let's see what it says more. Go back to your browser and check the community reports, which it didn't appear. And note, if you don't see the traffic, try to click the untrack button, refresh the page, and click the track button again. So we did it several times and we saw it in burp, right? So it was my third time now when I actually copied it. So we have a lot of them. Forward, forward. I'm just reading all of them now. So let's untrack and keep this going. So we saw that it got the message, right? To probe. So when we're doing this, if we turn intercept off quickly, I think they will appear, right? So just another try. The intercept breaks it. Track, send an 8, and forward intercept off, and then we get it, right? So intercept is breaking it. And we can actually track his car now. So we'll probably see another message somewhere. What's he doing? Where's my car? So we can send a message here too. Test. Where the glitch. So it looks like glitch's car here. So we can't see this here, but I'm kind of assuming we can see these in the history. WebSockets history. And here we can see all of these messages. We could have just went here to copy the message. And I've never looked at this, so it's new to me. That's kind of cool. Nice. So I've seen this exists. That's why I knew it was there. So what was I thinking? Right, what's the other part? So to server. To server. There. So the other one says track. What if we do something else on track? Like stop. Right? Maybe it can control the car. So it's just keeping track here. There was a hint. I'm gonna go look at the hint because I'm curious. So exploit the application and send a message to Mayor Malware while capturing the traffic. Okay, so we're going to capture sending a message maybe then. As Mayor Malware. Yeah. So we're gonna do it again with the send message. Yeah, I thought it was kind of something with this, so that's why I sent the test. But of course it will also be done through this. So I will try to tab, it just looked like the wrong thing there. So let's do intercept on. Let's I'm the bad guy. And let's click send on that. And Mayor Malware's messages, we don't have any up. But let's send that one on. Here, sender 5. Now we know it's 8, so we don't have to type his name. I was worried there for a second. And now we're going to forward and put this quickly, right? So let's see. Maybe we need to do it again. I hate parking meters. Yeah, so maybe we should just keep having them. So intercept on. And hi. And I did it on. Send. Forward. And sender. Great. And let's forward and keep forwarding, right? So we will see the data, if there's any data. 2. So we're getting the tracking data there too. 3 probe. 5. It doesn't look like we get anything from here, right? So the message that we're sending as Mayor Malware. So we got our own messages, right? So we're just going to forward this as ourselves. Yeah, let's test. So we get them back, right? So it should arrive even if it was ours. So if we intercept again, we do another test, and we send it, we change the data, and we forward intercept off. There, now we were quick enough. Just get it here. So, there. My name is Malware, Mayor Malware. Okay. Yeah, so this was a bit annoying that I'm imagining this kind of thing when you're actually trying to do a box and it's just not logical fully. But let's just see if we search for this in the WebSocket history. We must be able to search here, right? Can't we? Search. Is this just in this? So I guess I will do this. There must be a better way than this. Maybe I'm just blind or tired. Filter. Filter by search item. Let's just do THM, right? And this is just a text. And so we can kind of like hide outgoing. And let's see if we look at that. No. Maybe it's just all the keys here, or all the dude, where's my car? Dude, where's my car? Dude, where's my car? My name is Malware, Mayor Malware. Yeah, so we can find it here. Both of them. So I'm curious a bit why they're sending it twice, as flag 2 and as then the message. So we could also have searched for flag and just did that, and then we just get the flag messages. And let's remove that one. So, right, we've explored this a bit. It's not like we want to do more on this, right? Because it's was a bit glitchy with the having to turn intercept off quickly, and it didn't even mention it. But it was interesting. So if we untrack now, there. So I would be interested in looking at all of the data though. So if we remove this filter again, there, and we have all of the things. So if we just start at the very start of it, right? It's at the start. That's the tart. 2 probe, 3 probe, 5. We have time step sender ID. This is how we get those messages. And the message. And then we have 2 client, then 2 server, 3. So client sends 2, server sends 3. Client is 2 clients, or well, I should say to client message, to client message, and then to client again, and then it answers 3 messages, 2, 3 messages, 2, 3. Where is the position of the car? So it's probably not in here yet. Let's go to the bottom. We didn't turn on tracking. At the end we had tracking on, right? So let's just check. It is still appearing stuff. Let's go back a few minutes. Oh, right, we can see the amount of data here. Tracking update. XY. Yeah, this is what I was looking for. So here we have a lot of tracking updates going all the time. So there's that data. And then there's a message tracking data. So there's like 3 kinds of communication. We have the 1, 2, 3, we have the tracking updates and the messages. So ookie dookie. I'm actually closing burp. And if you enjoy this task, so well, the burp suit one, so I've done that already long ago. So now we have to wait. Now we have to wait for the next one, which will come at 17 tomorrow, my time. So it's currently almost 2. So I think I will have to read and get some sleep. So we have the Shy Hat and Cyber Warrior Studios. I don't think Cyber Warrior Studios really look at Twitch, so they don't notice a raid or anything. Shy Hat is probably doing like educational stuff, right? So science technology, education technology beginner. So it's very beginner stuff. I'll just hop over here while I actually click. First of all, let's mute the tabs so I don't spam someone with an ad or something. Now they're doing privilege escalation stuff, it says. So mine is kind of slow. I opened my own stream to look at who's online. Otherwise, you know, everybody's not always in the cybersecurity one. So maybe I should open this one too. Yeah. So I've raided the Shy Hat several times. Let's look at what they're